this is week 3. And today is going to be linear algebra, sort of, and over R and modules. And the idea is, how are we going to actually be able to really work with these things? And so the situation is that R is going to equal K of x1 to xn, possibly thinking of it as a graded ring, or maybe a quotient of that, K of x1 to xn, modulo some ideal. So R could equal this too. Okay, so these are 2 options. These are the ones, the stuff that sort of Macaulay 2 and other systems really sort of really hit. But we're going to be interested eventually in also thinking about other rings and how you might do linear algebra in these things as well. Okay, so here's the, so we're also going to consider matrices. So I'm going to write a matrix as R to the B to R to the A. These are just free modules, and I think of them as just the standard ones with a basis given by unit vectors. Okay, and then a matrix here. This will F is going to be, F is really an A by B matrix with entries in R over R. Okay, so this homomorphism from RB to RA, this thing, when I give you bases of these things, is just like usual linear algebra. And then I'm going to have another map also. G is going to be, oftentimes it's going to be R to the C to R to the A. And this G will be here also. So this will be an A by C matrix. And I oftentimes will write these as by columns. So write F is just the columns F1, F2, dot, 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 FA, I guess, is how many columns I have. And each FI is in the free module R to the B. It's a column vector. And similarly, G will be equal to G1, G2 to GB. Now, there's 4 computations that we would like to do with these things. And it turns out that if we just do these computations, we can get a ton of we can get almost everything done directly. So, so there's going to be 4 computations, actually really kind of 3. One of them is more of a 4 computations that we would like to do with linear algebra. Well, actually, what kinds of things do you want to do with linear algebra? If I give you a matrix, what do you want to figure out?
Sorry, Mike.
Yes.
For F, shouldn't there be B columns where each column is in RA?
You're absolutely right. I shifted these. This is in R to the A. Yeah, let's be careful here because they're important. So the image of each of the B vectors are going to be F1, F2 up to, and there are B of them. So there's FB. And then G, there's image of C different vectors, and they're all in RA. So this is up to G sub C, and the G sub I's are in R to the A as well. Okay? So that's, thanks for pointing it out, because this kind of detail is really important not to, you want to just get it and not think about it again. I used to be that when I was first learning this stuff, it was 50-50 whether I was thinking of rows or columns as the vectors, and I didn't have any real, skin in the game. I didn't care, but I also didn't choose one. And it was kind of a bit of a mess. So we're choosing them. The columns are going to be the image vectors of the unit vectors. Okay, so this is important that we have that. Now, what are the kinds of computations you want to do with this? The inverse. Well, actually, that's an interesting question. So that would have to, first of all, we'd have to check and see whether something's invertible and then figure out the inverse. But that's absolutely going to be a good one. But that's not the one we're going to write down first. That'll be done in terms of other stuff. Kernel. That's the very first one. So the first computation is the kernel of F, say. So in fact, we already talked about this. So of course, the kernel of F is just equal to what? It's equal to the set of how do I want to say this? Say H1 down to HB in R to the B. I hope I'm getting my my indices correct here. Such that what? Such that this times the matrix F is 0, and that turns out to be H1 times the vector F1. This is a polynomial. This is a vector, and so on to HB times FB is equal to 0. So this combination is in R to the A. Okay, so that is the thing. These things are called syzygies. They're kind of things lining up. So a syzygy of planets is when they become collinear, things like this. Okay.
So that expression equaling 0, that's what we're calling this H1 F1. That's sum.
H1 F1. So this is just if I take any polynomials, I can take it times the column. So let me write for the moment. I won't do this in general, but those things mean vectors, right? And these are polynomials. So I'm trying to find vectors that when I combine the columns, I get 0. This is a kernel of a matrix. Except for polynomials, it's a lot more interesting than in fact, it's bread and butter for commutative algebra. No, it wouldn't exist as a field if that wasn't the case. Okay, so this is what we want. So we want to be able to compute a generating set for this. So so the idea is we want so the computation is compute a generating set. For this. And the way we do this, I'm going to stylize it. I'm going to say, well, what is a generating set? It's going to be a set of vectors in R to the B, right? And it's going to be the image of some matrix. So I'm going to let sys of F denote a matrix, some matrix. The trouble is there's no unique one. So we can't say that. It's a computation that's going to give us one. Okay. Some matrix from where to where, the target is going to be R to the B. And the other, let's see, we're using A, B, C. So let's say it's R to the D to R to the B. Okay. And this is going to be sys of F. It's just a matrix. Let denote some matrix such that the image of the matrix sys of F, which is a submodule of R to the B, is equal to the kernel of F itself. Okay. So so one way to think about this is that we have a map. If I go the other way, I think of it as F is going from RB to RA here, and that's F. And then I take sys of F over here, and that's going to be RD, which is probably a bad naming convention, but at any rate, so this is exact at R to the B. Okay, the kernel is equal to the image of this thing. If it were not, if you didn't have all the generators, you just had some, then this would just be a complex. Okay. But if I have a complex, the image of this will be some, it will have to go to 0 here, therefore it will be contained in the image. But what I want is this thing here is going to be the computation that we're going to black box for now is that if you calculate that, you have calculated a complete generating set for the kernel of the thing. Everyone okay with that? It's kind of an important one. I like to do arrows this way, and the reason is if I take this as a matrix and this is a matrix, and I do it this way, the composite is just F times that. I don't have to keep switching them around in my mind. That's actually the main reason for doing it. That's why Macaulay 2 does it. Except it actually, there's a little more of a real reason for why it gets done. But, you know, not everyone, yeah, I mean, there's lots of reasons why it's good to do it this way, but one of the reasons that is not good is because everyone does it the other way to start. So, but nonetheless, I will oftentimes do my arrows this way. So maybe I should do an example of this right off the bat. I don't have one written down, but we'll do it. Actually, yeah, let's do a very simple example. Let's take R to be K, adjoin XY. And let's let F, this one doesn't involve G yet. It's just the specific matrix F. And F, let's say, is the matrix, it's a X squared and XY. So this is a 1/2 matrix. So I think of F as going from R2 to R or R1. Either way, I don't really care. Sometimes I'll put the 1 in, sometimes I won't. So we have this. So what is the kernel of this? Some of these you can do by hand. Most of these things are really tricky in some ways. Yeah, so if I take, so this should equal the submodule generated by some vectors, okay? So what is one of them? XY, did you say? X and minus Y like that? That's close. But in fact, this would be X times X squared minus Y times this. So we have to put it the other way, right? So this is Y and that's minus X would be one of them. Are there any others? Actually, negative of this is one, but that's in the submodule generated by this, and 5 times it is also. So we don't have to worry about that. But could there be any others? Well, you have to do some work. I mean, you have to say, suppose I have something times X squared plus something times XY is 0. Well, actually, the polynomial ring is a UFD. So if I have, if I take something times this and something times this that are essentially the same up to sign, they have to have the same irreducible factors, and consequently, you're going to find that this is the only thing that there is. I mean, everything else is a multiple of it. Okay, so this is this contained in R2, not reals, just R2. And so cis of F is just the matrix is equal to this matrix Y minus X, which I think of as a map from R to the 1 to R to the 2. Okay. And then the way I might write the thing is that if I have R mapping, or R2 mapping to R, which is given by X squared and XY, and then I take the kernel of this thing, I have one generator to it, okay? And this is Y minus X. Let's fill this out. Okay, what goes on the other side of this exact sequence? It's going, the image here has to be the kernel of this. So this is going to be R mod the ideal X squared XY. That would be one way to do that. In fact, that's the main way. And now, what's the kernel of this map? Again, this is a polynomial ring. It's a domain. So if I take some constant times this and it's 0, that forces the constant to be 0. So we get to 0 here. Okay. So this is equal to cis of F. This is F. This here is cis of F, which is 0 because there are no syzygies on that. And this is an interesting thing that Hilbert noticed back in the 1890s or 1880s. Can you see that, or should I write up this one here? Oh, the lap. Oh, okay. Good point. I'll try. Yeah, let me raise it up a bit. Okay. So online, can you see this? Isn't the handwriting okay?
Yeah, it's scrutable enough.
Okay. Well, if you need me to write larger, let me know.
For sure. Thanks, Mike.
Okay. So anyway, so Hilbert actually proved that no matter what I start with here, and I do cis of it, then cis of it, and so on, that eventually I'm going to get 0. Okay. And we'll talk about that later, maybe. But anyway, this is a good one. This is a pretty easy one at the moment, but we'll do some other ones in a bit. The second computation is actually kind of the same, but it's just a little bit more involved. So the second, so that was one, the kernel of this. The second one is I would like the following. This is going to be called, I'm going to call it what it, so this is what name we came up with a long time ago, before Macaulay 2, even doing Macaulay 1 stuff. In Macaulay 1, way back when I was like just a postdoc and things like that, basically everything was matrices. You just use matrices all the time. And that's what this is. That's why we, instead of just thinking of this as a module, I'm thinking of it as a matrix. And you know, I'm declaring that cis of F is 1. This is also going to be a 1. And what this is going to be a map from some space. I shouldn't use the same D over here because it's not that, but it's going to be from, it's going to be some free module of say E now, mapping to R to the, so remember F and G are what we have up here. R is, the F and G are both going to R to the A, but their sources are different. And in fact, this is going to go to the source, this is the source of F. Okay. So here's what I want is that the columns of this matrix will generate, so we want this. The columns of this matrix generate the following set. There are two ways of saying it. One of them, it's a set of vectors H. I guess let's sort of stay. I guess I use bracket sum and I use parentheses sum, whatever. They're completely the same for me. Okay, but let's do it this way: H1 to HB. Okay, in R to the B. Okay, that's this guy here. The columns are going to, every element is of this is going to be some element in R to the B. And what do I want? I want that so that the sum of HI times FI, and for the now I'll write a little arrow over the FI to remind us that it's a vector. Instead of being 0, I want it to be in the image of G. Okay. Well, what does that mean? Another way, this is equal to the set of H1 to HB in R to the B, such that, what does it mean to be in the image of G? It means that there's some other polynomials, say K1 and so on. So this is K1 times G1 plus dot 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 K something G something, and that's a syzygy on the F and G's. So this is going to be the set of H1 to HB, K1 to KC, because that's how many G's we have. This is in R to the B. There exists, so let me say it this way. It's a set of H1 to HB such that there exists an element in here such that the sum of the HI FIs, I could either say equals this or plus that is equal to 0. Sum of K sub J's times G sub J, and that's equal to the 0 vector. So these are all vectors, and we get that. Okay. So I don't know if it's worth, I wanted to write it out just so you actually see it if you're not really thinking immediately that linear algebra is exactly this kind of thing. But it's kind of interesting. We don't really need this computation separate. Why? Because if I can compute cis of this, I just take a look at, I just take all the vectors that I get from this whole cis and just take the first B columns, first B rows of that matrix. That would be totally fine way to do it. But there's some problems with that. It's easier. A lot of times, that's going to be very large generation sort of thing, and this might be smaller, and so on and so forth. So I want to do that. And so another way to say this, by the way, is that this is the columns. This is equal. So the image of here, let me say it over here. So the image of this modulo map is actually equal to the kernel of the map R to the B mapping to R to the A, but modulo the image of G. So it's kind of all of a sudden, instead of just doing kernel of free modules, we're doing a kernel of a free module to a not free module. Okay. So this is it's somehow a generalization, and one could say, well, why don't we just take a matrix that gives you the kernel of any map of things? Well, we're going to do it this way. Yep.
I think I'm probably missing something. Why do we have a B plus C vector living inside RB?
We don't. I forgot. I was starting to write it down, and I forgot to put it down. Okay. So is all the other notation fine? So basically, we take larger syzygies on the whole set, and then we lop it off, and we get this. Okay, and this is one way to think about it. It's really just a kernel of this thing here. The image of it is, at least. Okay, so that's one thing. Let's do an example of that. Do I have an example of it? I do. How about here ours? We're going to take these are just this is a simple example. We did the x squared xy, so let's just do it. This just is hopefully this is going to be R2 to R1 or R. And sorry, no, I missed. I forgot. That's not what it was. I didn't write down the rest. F is going to be the same thing that we had before, x squared xy, and that goes from R2 to R1. Okay. And now I want another matrix G. And I want this to be a 1-by-1 matrix, x cubed plus x squared y. So that's going from R1 to R1. So remember what these things are is that you have to have two maps that go to the same thing, basically. Okay. And now I want to do, I can do modulo in both directions. So what is modulo of FG? And what is modulo of G comma F? So remember how this works. One way to think about it, think of it as the syzygies on well, for F and G, we're going to concatenate it like this. We're going to take x squared, xy, and then x cubed plus x squared y. So what are the syzygies on this, on these three polynomials? I'm going to give you one of them. The first two, and then we put a 0 here. So one of them is going to be what we had before, y minus x, but now 0 here, okay? Since we're going to be lopping off the one corresponding to G, we're going to be looking at that. So y minus x is still going to be there. What else do we have? This thing is actually a combination of these two things. So really what we have here is we also have that 1 times this, actually say minus 1, is equal to, what is it, x times this, and x times the next one. That's one possibility. By the way, or you could also have it also, this whole thing is divisible by x squared, so I could have an x plus y here in 0, or y minus x 0, and x plus y 0 minus 1. I think that's right. If I take this thing times x plus y, yes, I get that. Okay? The reason these are not unique is essentially because we don't know which of those two to take. There's lots of ways of writing this in terms of these things. One could try to make it more specific, but anyway, there's that. So what is the modulo of FG? It's going to be all of it's going to be given by these columns. So this thing is going to be the matrix now. We can choose either one of those we want. I'm going to choose the second one, I think, is x plus y and 0. Okay. So what that means is that if it's the kernel, what this is saying is that the vector x plus y is 0. If I map it to here, mod the g, that is going to 0. Okay. And this one was going to go to 0 whether you mod it out by g or not. So it always includes the ones where you don't mod out by g, but then it will also include others. Okay, what about the other way around? What's modulo gf? So that's this is a, this is b, this is a, and now for b, we have to we do it the other way. We take the x cubed here plus x squared y, and then we take x squared and xy. And we want the syzygies on this. Well, they're exactly the same as the syzygies on this, just in different order. But one of the syzygies is 1, and then x plus y, I guess minus 1 and x plus y and 0, like this. And these are them, but we're taking the first row, and I don't care what the others are. As soon as I have a 1 here, the image is everything. So in this case, this is just the idea. This is a 1-by-1 matrix given by that. So remember that actually, is it a 1-by-1? So yeah, so this G and F is going to the source. This is going from something to the source of G, and the source of G is one-dimensional. Okay, so that's all it is. So this is kind of boring, except it's telling you about ideal membership in here. Okay, so these two things are going to be what we need for a bunch of syzygy things. Before going more into that, I want to do the other two things. Any questions about this so far? Online or here? Is the definition, I mean, it's a little weird, but hopefully the definition of this thing is actually okay. This is probably really the way to think about it eventually. But it's also nice to think about it in terms of actual polynomials and equations. Okay, the third computation is not really a computation. It's a predicate. So I guess it is a computation, but it's giving you an answer. So this is, we're again, all of these were given f and g basically, and they're both going into r to the a. So we might want to be able to determine if the image of f is contained in the image of g. Okay. So as an example, if f is well, I'm doing it the other way. I wanted to do this.
Sorry, we cannot see anything.
Oh yeah, can we press the thank you. Okay, can you see now? So we're determining if image of f or one of the, if I have two matrices that have the same target, I want to know if one has image contained in the other. This is a Grosvenor basis computation and for modules. Basically, you have to calculate a Grosvenor basis of this submodule, and then you have to check and see whether each one of these things is in that by reducing it to 0 or taking its remainder or something like that. So, so this includes ideal membership. If G is an ideal and that, but this is, I would call this submodule membership. Okay. And which of these two is contained in the other? So where are the two examples? Here. So is image of f contained in the image of G or vice versa? The image of f has two things of lower degree than this. There's no way it's going to be contained in this thing. By the way, notice that there is no notion of an inverse. Even this is a 1-by-1 non-zero matrix. It's not invertible. because unless we go into a fraction field or something like that. So anyway, but this one is the image of G is contained in the image of F in this example. Okay. Now there's one more interesting thing which is exactly closely related to this. In fact, I didn't even have this one down at first, but then I realized that we kind of need it when we're doing it. So here's the situation that if image of F is contained in image of G, okay? So that's the hypothesis for being able to compute this thing. By the way, let's rewrite the situation we have here. We have R to the B mapping to R to the A, and this is F. And then we also have R to the C mapping R to the A. I'll write it here as G. And the image here is contained in the image here. So what I want to compute, then we're going to have two different names for it. Lift of F along G. That's one notation for it, but that's not in Macaulay 2. Okay, the Macaulay 2 notation is F//G. Sort of divide F along G is the way you think about it. Is the following thing, is a matrix H from RB to RC. Okay, so let me see if I can do this. That's this thing here, and this is going to be H, and then there exists this thing here. Okay. There is a matrix H such that this commutes, such that F factors as you do H first and then you do G. Okay. And this is what we will, if I have given you the situation, we want this. This is actually a really important thing. Once you have this and these two things, you have all of homological algebra at your beckoning. Okay. Except for injective modules. And there you can have it in some cases, but the injectives are really hard in other cases. Okay, so so does this make sense? So let's do an example of this. Let's do the example we had above, but I want to do the one where I'm going to do the one. It's a little unfortunate. Sometimes I want for my example, the F to be one and the G to be the other. So I'm going to rewrite this. I'm going to say that let's let F be equal to x cubed plus x squared y. And that's going to be from R1 to R1. And here we're going to have R2 to R1. And this is going to be G. And that's it's a 2-column thing. So x squared and xy. Okay. So we have this guy here. And what we want is a map from here to here. Okay, do it as a orange thing. Here's H, which is F / G. So F lifted along G. And what is it? It's a 1 to 2 matrix. Sorry, it's a 2-row matrix by a 1 thing. So F here, F / G is exactly equal. So what does it mean? It means this polynomial is in the image of this. So this is just this is a certificate that that the image is contained in it. It's giving you specific polynomials that works, or ring elements. Okay, so here this is going to be what? I think it's x plus y and 0. Okay, but it's wait, it's it's R2 is the number of so the element here, 1 goes to x plus y 0. When I multiply it here, I get x squared times this, x cubed plus x squared y, which is exactly that. Okay, so this is really ideal membership. So this includes the notion of ideal membership, but giving me a certificate. Ideal membership certificate. Where, in other words, the actual polynomials that will give you that polynomial, this polynomial inside of this ideal. So that can be very, very complicated to compute, and that you absolutely need Grosvenor bases for. So sometimes there are no other known algorithms. That's probably not true. There's probably other known algorithms, but that one works pretty well. Okay. By the way, this is something that if you've done homological algebra, you know this this kind of thing. So let's say something about that. Recall that an R module P is called projective if whenever we have the following situation: M maps to N maps to 0. Okay, so this is a surjective map. Then what's the situation? P, and if whenever we're given this, where this is exact at N. In other words, that's a surjective map. Then what do? We can lift it here, and then there exists a lift here, such that that this is equal to this. Okay, so let's give these names here. Let's call this phi for the moment, and I don't know, f or something like that. Maybe I should call it g. How is this anything like that? So above, if we're given if the image of f is contained in the image of g, then what we have is the following situation. We have r, what's the target source of f is r to the b, and that maps down to the image of g. Wait a second. How do I want to say this? Yeah, image of g. And what is this coming from? This is r to the c. This is the same map as g. It's just going into the image of g sitting inside of that. And this is surjective. And sure enough, the r to the b, this is if this is f, except it's really f is going is sitting inside of r to the a here. So that composition is f, and this composition is a, but in both, is g, but in case both, so if I'm going to write this as f and g, but really f is the whole map here, and g is the whole map, and then this is f // g. In other words, what this is doing, we know that that all free modules are projective, and this is implementing the projectivity of free modules in the case where we have a sort of nice map. Eventually, we want it for all of the m to n's that we have here, and that will be an exercise essentially. In fact, right now with all the stuff here, you could do that exercise. But we're going to talk about it first. Yep.
What's the name of the map from P to N? Can't quite see.
P to N. I wrote it as F.
F. Thank you.
I don't, and I'm not really saying what it is. That's an H. And I should say such that that f is equal to, I first do h and then I do phi. Okay, so I get commutativity of the diagram. But actually, I'm not. I just chose some names right there to put it in to say it. I'm not. That's probably not a great naming scheme for that. Anyway, these four things allow you to do almost everything you want with modules. Okay. Before we say all about that, I do want to do one more example. So this one we have done an example. I guess we've done an example now of all of these things essentially. So so now I'm going to come back over here. So if we can switch the camera. Is that okay if we switch the camera online yet? So
just a few seconds. If you could.
That's fine. I'll start erasing this over here first. So what is it that we want? We're going to talk about modules in a bit, but first I want to just go through some important aspects of this. So here is an example, except that this is more of a construction than an example. Okay, so tell me when you're ready for that.
Yes, I think so. Thank you.
Okay, good. Okay, so the example is, suppose we have it's going to be computing x I of R mod I into R. Okay. This is going to be the first computation. I chose this one because these are really easy to write down how to compute. And they are really the most important of the X modules that there are. And if you understand these things at an intuitive polynomial level, it's really cool. Okay, so that's my personal feeling about these things. But we'll say what they are in a bit. And later, we'll do this for I for m equal. We'll replace R mod I with M. It's the exact same thing. Replace R mod I with any finitely generated M in R module. But we'll get to that in just a bit. But I want to say, how do we do this? First thing we do, so how do you actually compute this? I'm not expecting you have really necessarily seen this. Even a T. McDonald doesn't really, it sort of has this stuff, but we have to do all the exercises in order to see it. So, but nonetheless, it's pretty straightforward. The first thing you do is compute a free resolution. At least out to a certain point if you only want one of these things. A free resolution of R mod I. How do we do that? Well, we haven't talked about how to compute any of these things yet, but it's all done by Grubner bases, okay? But we compute it, so I'm going to do this one backwards like this, or rather forwards. Another reason this is good is you sort of what you create as you go, it goes along the page the way one might actually write it. So anyway, we have this, and we have R to the I'm not going to call it R to the A anymore. I'm going to call this one F0, which is just R. I'm going to call this one F1, which might be the R to the, if this is going to be F, I'm going to call it del1, and I'm also going to call it F. Okay, so this is just going to be a bunch of polynomials that define I, where the columns of I of F generate I. In other words, the image of this map into here is this, and F0 is R, and F1 then I guess is R to the B. If we were using the same notation we did here, R to the A here is F0 is R to the A, which is 1. A equals 1. Okay. So anyway, so the columns generated, and now what do we do? So we were given this to start with, and we just do sis of it as we go. So this is just sis of F, and we'll call that equal to so delta 2. So delta 2 by definition is going to be sis of F. Okay, and then that gives us these FIs are free modules. FIs are free R modules. And they're all finitely generated free modules. Okay, so so these are all matrices. So this is just this matrix, and now we take sis of this. This is sis of F. So this is sis of delta 2, which is delta 3. And so delta 3 would be sis of F. Except that you have to use the same one that you have here. Okay, so it's really just sis of that. And then you can keep going. Okay, for some rings, for polynomial rings, it's a theorem that this will stop, but in almost all other times it will not. Okay, so that's the free resolution. This is step 1. And actually, we only need it out to a certain point if we only want one of these. Okay, step 2. We apply HOM of dash comma R over R. This is exactly, for nice free things like this is exactly like the vector space situation. What is applying HOM of doing it? Well, we will define for M a module in our module. M star, by definition, is HOM over R of M comma R. And this is in the dual to M. R dual, maybe, if you want. But anyway, this is the dual module. It's kind of like the dual vector space. And then if I apply it here, what do I get? I get F0 star. I get F1 star. First of all, what is F0 star? R star is just R. R to the B star is just RB. You know, it's just, but it's the usual thing that it's the dual vector space. So you have to choose bases, but we already have bases chosen. So, we can do that if we want. And what are these maps? First of all, those are going this way, but these are now going this way. So F2 star. And it keeps going. Let's go to Fi star and keep going. Okay. What are these maps? This is delta 1 transpose. This is delta 2 transpose, and so on. This is delta I transpose and delta I plus 1. Okay, now let's make sure I have that right. Yes, I do. Okay, the indexing should always be there. The indexing of delta sub I should always start at F sub I. That's a sort of a good thing. And of course, when you dualize it, it's not going to be that way because it's going, it would be indexed from that. Now it's indexed from that. So it goes up by 1 or down by 1, whatever. And so we have this, that's step 2. And then step 3, we compute homology. So X I of R mod I into R, or M if we want later on, this is just the kernel of delta I plus 1 transpose mod the image of delta I transpose. That's all it is. And in some ways, if you think about it, what are you, well, maybe we'll do an example of this if I have one. But anyway, these things are very cool. And some of these are 0. Some of the very first one that's non-zero is called the canonical module of R mod I, and so on. So these things tell you an awful lot. Not only do they tell you an awful lot in commutative algebra, but these are the basis of sheaf cohomology as well. So so these things are used all over the place. Now they're not totally trivial to compute though, because you have to go all the way out to the ith step. And then to calculate, if these things have large ranks and you're calculating the kernel of this thing, that can be really hard. In fact, it can be really hard. And so sometimes you have to avoid doing that. Anyway, this is one of these kinds of things. But we haven't, so I said we're going to say how to compute it. But we're not ready there. So we use SIS to compute those things, okay? In Macaulay 2, you would actually use res or free resolution or something like this because it's using a faster algorithm than just doing it one step at a time. But this would work, at least on reasonable sized examples. So we have that. This is really easy to compute. We just transpose all the matrices. There's no computation going on here. And then step 3, there is some computation. So we have to figure out how to compute the kernel mod image of this thing. So let's do it. So did I already do that one over there? Yes, I think I did. So we're almost ready for that. And then we're going to do an example of it by computer, I think, in a bit. But first of all, so we need that given so I'm going to write this, this part here is just three matrices, sorry, two matrices and three free modules. And I'll call them R to the A. I'm going to do it this way just to match that, I guess. No, I don't really want to. Doesn't really matter. These are going to be R to the A, R to the B, R to the C, say. Okay. And I'm going to call these two matrices something. Here they're just the transpose of whatever these things are. But I'm just going to call this one F and this one G. Okay. And I'm going to assume that this is a complex. So what does that tell you? That tells you that that F, you do G and F, you get 0. But you don't know it's exact. Okay. In fact, that's what this is measuring, is whether when you flip them over, here, when you do this, you're getting all of the solutions each time you calculate the acidicities. Here you flipped it over, now you're trying to find the solutions. Do you have anything new? So we're assuming this is a complex, which basically means that the image of G is contained in the kernel of F. Okay. So how do we, and what we want is the computation we need, we want to calculate the kernel of F mod the image of G. Okay. So how do we do that? Maybe we should do an example first. But let's think about this for a second. This is the kernel of F mod the image of G. So if I want the kernel of this thing, but anything coming from here, I want to be 0. So one thing we could do is we need the kernel. Okay, so why don't we take cis of F and we'll get something in here. So maybe I should put it up here. So we're going to get a R to the D now. And that's going to map down to here. And this is going to be the cis of F. Cis of F. Okay. Ah, now it's kind of interesting. We have two matrices going to the same target. All the numbering is different from what we had before. That's just going to be the way it is because we're doing things at different places in the resolution. But we have this and this, but they come in. One of these things, the image is contained in the other one. What is it? So the image of G, so kernel of F is actually equal to the image of cis of F. Okay, so this thing is contained inside of here. So I guess that means that we could do a mapping up or something like that. We could do the lift, for instance. Since this one is contained in the image of this, we probably get some map here. That just means, you know, we need to do an example. We'll do it in just a second. But I don't want that. I want the image of this now mod the image of this. So now we need the image of cis of F modulo the image of G as a module. I think I'm going to leave this as something to do during the project session. But it's going to be. I can actually say what. Maybe I should say what the answer is, and then you can do it, or would you rather think about it? Because I can. So try modulo of cis of F, comma G, and that should give us a matrix that will be related to this module. Okay. Let's do an example. Okay. Share. Okay, can you see that at all, or do I need to make it larger? Oops, let me clear. Restart. Okay. What I want to do is I'm going to do this. Okay, let me make this larger too. Okay, I'm going to do the rational quartic. This is one of the ones on the sheet for problems listed. I gave 3 different ideals that one can do. So here, if I do R is equal to just a polynomial ring in 4 variables over some Z mod 101, it doesn't really matter. You can do it over Q if you want. And then here is the ideal. And if I look at the generators of I, actually I get, so this is written in a very compact form. BC minus AD is the quadratic, and that C3 means C cubed. So coefficients are in front, and then exponents are after the variable. Okay.
It's B2D.
B2D is B squared D. B squared D. So if you have a monomial, you always put the coefficient up front, at least in this way of doing it. You don't have to see it that way. You could also do it. We could also do netlist I underscore star. I underscore star is a list of all of them, and netlist makes a nice block. So you get BC minus AD, and there's CQ minus BD squared, and so on. It's just that for matrices, it can get, if you want to get any information out of it, you want it as compact as possible oftentimes. Okay, so now just using, okay, these commands, sys and modulo, are actually commands in Macaulay too. So so here, if I do sys of f, I get 4 things. And if you think about it, this is kind of interesting. Oops. Each of those columns, c squared minus b d0, is a syzygy on those things. Which is not at all obvious. I mean, to actually compute it, you might find with some effort that these are them, but then you have no idea if you've got them all. And it turns out that that's the great thing about Grosvenor bases, is they give you a way of being sure that you've got all of them. But otherwise, it's really quite hard. And I will talk at some point about the Buxbaum-Eisenbud, what makes a complex exact, because in fact, when we were trying to debug this before there were any algorithms for computing resolutions anywhere, how do you know if it's correct or not? So you have to bootstrap it up, and so you have to check other ways.
So you said that sys of f is not unique.
No, because I could have had a combination of 2 of these columns and put that in as a, up to a change of basis. It might be, but if it's inhomogeneous, there's no notion of minimality. So you might have a bunch of things, and you don't know if you need them all or not. It picks it using Grosvenor bases. So what it does is it does a Grosvenor basis, which we will talk about a little bit in there, and then it uses the syzygies for it. It gives those, and then it chooses what's a minimal set of those.
So given a Grosvenor basis, the syzygies.
No, and it's sort of, you can choose it in a minimal way. You can choose it in a normal form way so that you get exactly the same ones. But those are going to be a non-minimal set. If you want to take a minimal set of them, you have to choose some of them. And that is not, maybe there is a way of making that well defined actually, but it's not implemented that way.
So is there like a default Grosvenor basis it picks?
It uses the default, if you have a polynomial ring in Macaulay 2, is always to use the graded reverse Lex order. If you want any other one, you have to actually give it directly. Okay, so here we have, this is the syzygies. And are there any syzygies on those 4 columns? Like, are there polynomials of 4 columns such that the first polynomial times the first column, second polynomial times the second, and so on, add to 0? Okay, well, we can check it out. We do sys of f, and sure enough, we get a minus. Sys of f is unique in Macaulay 2, so it will give. You don't know how it's choosing it, but it's giving you something. You do it again, it'll give you the same thing. Okay. But anyway, so here it is. It turns out that in this one, a times the first column minus b times this minus c times the third plus d times that is 0, and that's the only one. And then, of course, if you do the next one, it has to be 0 because you can't have a kernel of a map from an R1 without it being the 0 map, and it's not the 0 map. That's for a domain.
Good question.
Yep.
You said that Macaulay 2 is computing roller basis to do this.
Mhm.
So if we change the monomial order, does it give us a different syzygy?
Absolutely.
Okay.
But the thing is, if it's homogeneous, it's only mildly different. It's but if it's inhomogeneous, it can be wildly different. I mean, it'll still generate, but there could be very little relationship between them. Whereas in this case, it's giving you a minimal set of generators, and that means that there's an easy change of basis that goes from one to the other, back and forth. In other words, the free resolutions will be isomorphic that you get, which that's always true. But I probably don't need to do this way, but I'm gonna. There's a new package that Greg Smith and I have been writing, and it's in the system called complexes, which replaces a lot of the chain complex code in Macaulay, in the Macaulay 2. Mostly you won't notice it, but there, unless you were really delving deep into into it. So here is the free resolution, and here are the maps. So it's probably exactly the maps that we saw before. Okay, so here are the three maps in the free resolution. And then we could calculate, we can take the transpose, so the maps themselves, like c.dd underscore 3 is this one, just one of the matrices, the third one. In fact, actually, if I write on this, you probably can't see it yet, so I think I'll wait. And then what we want to do is take the kernel of one of those, mod the other. So there's two ways. So what we do is we take here, I'm going to take the cis of transposing that matrix, okay? So that is coming over back here, that is taking the transpose of the current bounding matrix in the free resolution. And then I can take the, I can look at that one and the, so F is the syzygies, and then c.dd underscore 2 is the image that we're taking, except that, actually, I think I didn't want it this way. I have to take the transpose. Let me, oh, I did transpose it, good. So I took transpose of c.dd underscore 2. So this is the transpose, and so the images, all four of these should be in, oops, how do I? Here, let me just do it this way.
What is?
C.dd are the differentials in the complex, and underscore 2 is the second one in there, and 3 is the third one. So we're taking the we're transposing the second and third one, and we're going to take the kernel of that one, of one of them, mod the image of the other. And sure enough, here's the kernel of the one map. There are 6 guys here, and there are 4 in the image. And if you look at it, you can see that the last, this AB 00AB is already in the image. In fact, because it's a complex, each one of those 4 has to be in that thing. Okay, and now if you do modulo of this thing, which is my naming is such that I called F to be the cis thing already here, and I take modulo of that with respect to the other matrix, which is transpose of this. What do I get? I get a matrix that is going to be a presentation matrix of that module, which we will talk about a bit more after the project session. But in fact, if you look at it, it's really not minimally generated. This thing seems to have 6 generators with every column here being a relation. But the first 3 are telling you that you don't need 3 of those 6 generators. So you can prune that out to get rid of it. So if I do prune of co-kernel of that, I get this. So this X module is generated by 3 elements, and it has 5 relations, which are the 5 columns of this thing, which we'll talk about a little bit later. And if you want, in Macaulay 2, you can just type x2 of r mod I, comma r, like that. It has to be r to the 1 mod I, because otherwise it thinks it's a ring and it gets confused. Okay, and then that is pretty much the same. In fact, it is exactly the same thing as that. So this is the canonical module of the rational quartic curve in projective 3 space. Anyway, I think, so what I want to do now is we're going to take a break. I think it would be good if people have what can present some of the problems. We can talk about who will present. And then we'll do that for a little while, but not huge amount of time. And then after that, we will we'll try a couple of the problems on here. I think we're ready. We're not quite ready. Might want to tell you one more thing before doing it, but so we'll anyway, this is the plan of events. First, a 10-minute break, and then we'll do some exercises, and then I might show one more thing about this, and then we will do a little bit of problem solving. Okay, that's good. Thanks.
Question on syntax.
Yes.
You got transpose C dot DD underscore 2 comma F. What does that mean?
Oh, I was just putting both matrices on one line. So it's just this thing comma that, and so it's a pair of things.
Watching this would be really nice if you could do this in a notebook.
Yeah, I know. And so we're working on trying to get such a thing back up and running. It turns out that we kind of have it, but in fact, I can give you the code for this too, and you can try it on the web version of it and so on. So, but you're right. Having a Jupyter notebook would be great.
You're kind of cutting your real estate in half by having like 2 windows.
You know, actually, I really like to have it that way because when I'm really doing research on it, I have what I'm doing here and I have my results, and then I can redo things extremely
You
easily.
just put them in the notebook, like you.
No, I know, but then it's hard to know what things are, it's just,
I don't follow you, but
Yeah.
because like you see immediately the expression, you write an expression, then you see the result. So like it's all linear.
there's a lot of,
You've got it.
it's linear when you're doing it that way, but now if I want to change it up and everything, I have to go find the commands that I did and change them and stuff. No, but how do you find them? I mean, suppose I want to choose 3 things. If they're right there, just, anyway,
But the notebook
I
is like
understand
another
that.
whole file. It's just like you combine.
Actually, that's a good question. So can you check it in to get easily?
Oh, absolutely,
Yeah, okay.
absolutely.
Without the answers though, right? Because that
can-
would be
Okay,
not
so
good.
there's a clear all results command. So like if you want to put your notebook in,
Yep.
You've been running it, so there's a command, clear all cells. It just empties out all the cells and then you can check it in.
Yeah, no, I understand, but there's something, it's just so, it feels much slower to me than when I'm actually really doing stuff. But I understand that that's a useful thing.
No, I've been using them for years.
Yeah.
Doing data analysis.
Yeah, right.
It's like they're really nice.
So in fact, we'll, I think that what kind of, you have a Mac?
Yeah.
Yeah, so it's on a Mac that we're having trouble with it. So it works under, but I think that that someone had an idea for it. So hopefully we can
So what was the
figure it
problem?
out.
Like, did it break when?
When Jupyter upgraded
did
their notebook
the
setup,
version 3?
it just none of the other stuff worked. It was just a breaking
Yeah,
change. And the person who wrote it is in industry and isn't around to sort of just say, oh yeah, this is an easy change to do that. So really what we want is a language server. That would be the easiest thing. Not the easiest thing, the best thing, but we don't have that yet. So so we have to do something. Yeah, it would be nice to
there's two
do
ways
this.
go.
Yep.
So the notebook framework is kind of agnostic. It's not, it doesn't depend on Python or anything like that. You can
Right.
plug in a language server, but then the language server has got to be able to produce output that will render nicely in the notebook. So
Yeah, that's not so bad, actually.
then the other way to do it is.
We already have a version for the web.
Can I call it?
Yeah, sure.
Or are they on the web?
They are on the web, I think, at this point, but
But your output, like,
Yeah.
Macaulay 2 program is producing ASCII, going to ASCII text out. So that.
the one in Emacs is, but the other one is producing HTML output, for
Yes.
instance. So or actually mostly HTML output, I think. So it's using and it runs through Kotek so that it will display math. Kotek, do you know that? It's a LaTeX for the web. It's like MathJax, but it's a little faster.
What's wrong with checks? Just historical.
I don't know. That's the older version of it or something. So Kotek is the newer version.
What is it?
That's what I heard. Is that true? Do you know?
Is there something replacing LaTeX?
No, no math check.
No, it's not. But actually, that's a good question. I thought it was improvement over
How do you
MathJax.
spell
I think it's faster or something like that. But I'm not actually now. I'm really not sure if that's true. I have to
what's-
Katex, Kotek. But it is true that
MathJax is
MathJax.
sponsored by the AMS, so it's got
Oh, I see. Okay, so maybe
stability behind it.
yeah, actually that's true. That's an interesting point. Actually, now I'm a little unclear of if I've got that wrong.
K-A-T-E.
I have to go and check and see.
Fastest.
This is embarrassing, but what is MathJax?
It's if you write in a HTML file and you just say $sign and then put some stuff and $sign, then it will it gets run through MathJax or Kotek, and it will take that and put it into a rendered math formula kind of situation, and do it on the fly.
Oh, it's by the Khan Academy.
Aha.
That's interesting.
I don't know what the difference. I
This claims
haven't thought about it for a while. Might be faster, but that's interesting. If the other one is actually supported by the AMS, that's a reasonable idea to use that. I'll have to check with the people that
claiming it's
use that. But is it equivalent? So, you know,
I
like
would assume it would take the same mark. But it's just like
the trouble is it's not all of LaTeX. You know, it's the math part, and it can get confused if it's too complicated. So you have to be a little careful. But for the complexes package that we've been doing, Greg and I have been using it, and it's been rendering, you know, sort of commutative diagrams pretty well. So.
So I actually took a course like this a few years ago.
Oh yeah.
where
In
I got
fact,
exposed
I
to
was
that.
going to teach. We're writing, you know, a book on this kind of stuff, and I was going to teach that, but then I heard that he had just done it a
Well, he
couple
wasn't
years
really
ago.
teaching, too. It was
No, I know.
computational.
Yeah.
But using-
Yeah,
Well, he was writing up pretty good notes.
yeah. No, I know. So I taught from that also. I taught using that at Cornell about 2 years ago. Or maybe even just 1 year ago now that I think about it. Feels like 2 years. Yes, I think that they should be on, let me leave this.
All the where the videos are.
Yeah, they were like posted below.
Oh, okay.
So if I come over here,
Yep,
there,
Okay. All right, thanks.
okay, I don't know where mine is located.
lecture 3 and then scroll.
Oh yeah, here it is.
Yeah, I don't know if you had previous ones. But yeah, I think like from the.
It says slides, but it's not
Yeah,
slides.
okay.
I don't know how to change that. So it's-
I ask you a quick question.
Sure.
I want to make sure I think we're going crazy. When you're writing these linear combinations here, shouldn't the F be first if you want this to be bold? Because aren't you doing this is a B by 1 matrix, and this should be a by.
No, this
Or
is a
minus-
polynomial times the whole vector.
Mm,
It's not a matrix
Oh,
multiplication.
this is H. Oh, sorry, this is the entry. Sorry, this
Yep.
is that. All right.
This is really just the
Yeah, yeah, yeah.
matrix multiplication of
Right.
H and F.
Sorry, I misread the H of the
Yeah.
vector. My bad.
Yep,
Something
sure.
Be pedantic.
Sure.
So in step 3, would you call that just call homology?
Yes.
So you said this is a very useful thing, computing X.
Yeah.
But is this construction natural in some way? Like it seems to, like this presentation, it seems to come out of nowhere, like we take some duals.
Okay, so here's what's really going on with this kind of thing. First of all, you can get totally different free resolutions, some minimal, some not, whatever. You do this and then you do this. These are invariant. These modules up to isomorphism of modules are the same no matter how you do it. So in that sense, it's uniquely determined by the R mod I itself. That's the thing. The other thing is this totally general process. If I have any sort of, in this case, it's a left-derived contravariant functor. But anyway, so you have that. You always do this. You do a free resolution or an injective resolution. You apply the so do that. You apply the functor, and then you take cohomology or homology, and those are the derived functors, and that's exactly what this is an example of. But you know, when you first do that, that's a lot of stuff, and these things are really basic, much more basic than that. So I think it's worth seeing this directly.
So if I have a simple, say, ideal I, and I do this for R mod I.
Yeah.
What should I expect the X particles?
So what's going to happen is that if it's a codimension C in projective space or affine, and you know the ideal has height C or is codimension C. The first until it gets to C, they're all 0. Okay, then XC, the first non-zero one, will be the canonical module, which if you look at its annihilator is going to be R mod I. Okay, at least in lots of nice cases. Say I is a prime ideal. And then all the higher ones are going to be very much simpler than that. But and there's a lot of uses to those things. So this one, yeah, we'll have to get there, but about that. But I'm gonna go get some water. I'll be right back.
Sure. And so I don't even know how. Okay, so where are we at now? So this is all fit up there.
Okay.
Who's interested in presenting?
Yeah, I worked through some of them. I'm confused about a couple of them, so maybe not presenting one of those.
Okay, that's fine. Anyone else interested in presenting? If you want. I don't want to spend too much time on it anyway, so, but,
I think I'm out.
You want?
I'm out this week, sorry.
Yeah, okay, that's fine, same as me. Okay, so which ones are you thinking?
So if you want like, for example, so K would be QQ.
Or I have it right here.
Or you could just replace. Yeah, and then exactly what you put in there. Yeah, just.
Why would I want a QQ and not R?
Oh, you can
So
do
I think we did three
just leave it in there. That's real.
I went through two and I
Change
was
that
not
a
sure
little bit
that.
and what
and I
you're
did,
calculating, but like these things. can be over-
Field.
Yeah, like any field.
Okay.
It's probably the same.
A, B, and C?
A, B, and D.
Yeah.
And D, okay.
I was confused by,
Got 'em right. And now I want to set it.
because it looks like if we're
And do I?
mapping Y to Fi as an equation, should this be mapped
No,
to R mod I?
I think you can just use round brackets. I usually do ideal and then.
okay.
Kernel of the ring map.
And then I would say.
Oh.
Set.
So here we did the
Ah,
kernel of
you
the
have to
ring
do
map, here,
X.
right? But now I is some ideal. And if you have this, you can compose it with R going to R mod I, and then you want the kernel.
Yeah.
Yeah.
You got an idea.
Now is the first step.
Does that make
So-
sense? So
so just
the
do
way I
three
would write that is.
So I don't know how
I
he's doing. I
goes
usually
to
do
Fi,
red, but I think he.
or Fi bar, or Fi plus. I tend to
I don't know.
ignore the, I just call it Fi,
Yeah.
and it's just a question of where it sits.
Is the way I think about it. So this map, the image of this map is in our.
Yes.
Okay.
I don't.
So you want the kernel of that map. That's the point. And I should have, but that is actually right. That should be an R.
Okay.
That was, that
Well,
was
yeah, you
actually.
could also do.
Yeah, I should notice. But we'll, see what time is it here?
I think we're now at a 15-minute break.
Yeah, and has it been
I don't
15
think you
minutes?
can
Yeah, I think. it-
Well, you said 10 and it's been 15.
Oh, I see. Okay. Oh, okay, got it. Okay, here, I'm gonna let you put this on.
Okay.
So when you're doing it, say your name when you're
Okay.
beforehand. And
Sure.
then here, you can put this thing should just be clipped up close to your.
Okay. And then what do you want me to?
Re-erase some stuff.
Okay.
Um,
What would you like me to go through?
I think that what's, probably the most important ones. Well, actually, A, B. Actually, A, B, and D are all, would be all good. If, yeah.
Yeah.
Here, let me erase something. We do it in the middle here. Okay, we're gonna start in just, oops, I don't. Okay, can you hear me? Okay, we're gonna start in about 1 minute.
Oh, I do remember how to do B. Okay. I was like, I don't see my notes, but I remember. We're gonna do question for A, B, and D
From the last.
from the last time.
So you can
Okay,
just-
can you hear me okay on 9?
Yes.
Okay, hello, I'm other Mike. Pleasure to be here. I think the plan is to go through a couple of the problems from last week. We're starting with 4A. So we're given ideals I and J in our polynomial ring R. And we want to compute first off I intersect J. And we want to do this doing elimination theory. So the one trick we know in elimination theory is we want to introduce a new variable and then get rid of it in some way that gives us what we want. So I guess I'm going to just claim right off the bat that if I extend my polynomial ring to include a new variable t, or I guess I want to intersect in a minute. I want to get rid of this variable t. When I bring it back into the original ring, I want to look at some multiple of t I by some new variable t, and then sum that with 1 minus t times j. So I think the algorithm follows from this claim, this equality fairly easily. We started with a generating set for I and j. The generating sets for ti and 1 minus tj are just scaling the generating sets by those coefficients. So then we compute a Grosvenor basis with respect to the usual Lex order where t is, I think, biggest, and then we eliminate t by just taking the ones from the Grosvenor basis that don't see t. So really, this claim is all we need to compute the intersection. Are we happy with the setup? So I guess I should say that this is
Is this on?
Where does this live? Do you want me to go?
Um, No, that's good. This kind of thing, where you add these variables can be, there's lots of tricks involved with this kind of, that you can do this exact thing in lots of situations. In fact, you'll see probably more in just a bit. By the way, what we were doing earlier today, you can also do intersection using syzygies. But we'll see that too.
Should I go through this claim or?
What do you think? Does anyone?
I don't understand that.
What?
I don't understand that. Sure.
Okay,
Mhm.
yeah, then.
So
Maybe.
I think it's, maybe one direction is clear. I think if we start with something that's in here. I don't know, let me get my. Maybe I'll show some details. So if we start and we let, say something in the intersection, this is definitely going to be in the variables x1 up to xn. So all we need to do is show that it's in this sum.
You've introduced T. That section will depend on T.
That's right. Yeah, so f doesn't depend on t. And because f is in I, that tells us that t times f is in t times I. And f is in j. So 1 minus f is in t times, 1 minus t times j.
Sorry, what minus that?
1 minus t times f. Thank you. And then we will write that f is, yes, tf plus f minus tf, and factor this as tf plus 1 minus t times f. And this is in t times I. This is in 1 minus t times j. So this whole thing is in ti plus 1 minus t times j. And that's that inclusion done.
So everyone understands how to use it, right? You just add a new variable t, you put an elimination order on, it doesn't have to be less, but where you eliminate t, and then you form this ideal, you go on the basis and select out the elements. So
The other direction is trickier.
okay.
Yeah, that was the one inclusion. The other inclusion, we start with something in on the right hand side. So we'll let f be something of the form ti plus 1 minus tj intersect, or just get rid of t, I guess. And because it's in the sum of ideals, I'm going to write it as the sum of elements in these ideals. So I'm going to write it as, say, I've got, maybe I'll use p x t plus q. So I want to sort of emphasize that we've got all these x's and then we've introduced this new variable t and we want to keep track of them separately. So maybe this is like a vector of variables, but I won't write that. And I said that p is in t times I and q is in 1 minus t times j. So because p is in ti, that means that, well, it's really of the form t times something else, where maybe call it p tilde, where p tilde is an I. And in particular,
That's not quite true. because it could be combinations of the generators of I
Mhm.
with T's in.
That's right. I actually, maybe I don't need this. I don't think I need to write that. What I want to say is that, well, what I want to claim, oh yes, okay, so what we still know, maybe I should ask, what we still know is that we have a common factor of T that we can pull out.
Not
From-
necessarily, actually. It could,
Mm.
all you know is that P of xt is a sum of all the generators of I, where the coefficients in it are any arbitrary polynomial in x of
Mhm.
t. And that's what you know. I mean, but on the other hand, this has to be true for every t.
Right.
So
So what I want to do is I want to plug in T equals 0 to conclude something about Q. And what I want to claim is that f of x0, I want to say that this is 0 plus Q of x0.
actually, I probably led you wrong with what I was saying. It is the case because it's in t times I.
Mhm.
That means it's in.
Right.
It has a t factor plus the sum of all sorts of stuff.
Mhm. Right, so because we have this T, when we have an element of T times I, that means this whole polynomial vanishes when we plug in T equals 0.
And this is just an identity of polynomials,
Mhm.
no mod anything, so.
Mhm.
yeah.
So this says that this is, I want to claim that this tells me that f, which is Q of x0, is in J. And you can do a similar trick that if I plug in 1, so now I'm killing off, if I plug in 1, I get 0 in front of the Q. That tells me that, or this is also again going to be P of x1 plus 0. And that's telling me that f looks like P of x1, which is in I. So they have to, so f lies in the intersection. So that's for A.
I can't see you on that.
Oh, I think,
see, okay,
yeah.
good.
Mhm.
Any questions? You don't get it?
Yeah, like what? I mean, the problem is to compute the intersection of.
So shall I write down
Yeah,
an
maybe
algorithm?
write it down.
Yeah, okay. Which board should I erase?
You can use one of these boards over here.
Okay.
So when you use compute, does that mean you just really open basis for it?
Find a generating set. Oftentimes that generating set will be a Grosvenor basis for it, but it might not. In this case, think about it.
So how is, so you haven't displayed a generator.
Well,
So that's what I'll write down here. So the question,
the
yeah.
key point that how you get I intersect J in terms of adding a variable t and then eliminating. So now you have to sort of write down how you actually do the implementation.
So I'm going to take algorithm for intersection. Of ideals.
That's for that,
Mhm.
that statement.
Yeah, I guess the proof was for that claim about the set equality, and now we'll do the algorithm, and the correctness for the algorithm will follow from that claim. Okay. I guess I was before you asked for the algorithm. So, but this is good. Okay, so I'm going to take its input. Ideals I and J. in a ring R.
Write down.
Yeah. So let's write. Do I have? I do. F1 up to FR, and J can be. I don't want to use G because it's not a Grosvenor basis, so I'll use H. I think that's the convention you've set. G's are Grosvenor.
You know, it's tough because we don't have that many letters.
Yeah, and only so many letters are good for polynomials. Like I've used P and Q, and now I've used F and H, and now it's G, and then we're stuck. Okay. Sorry. Okay, so I think what I want to do is I'll notice that, or I'll write that Ti. I'm gonna let big K be the ideal Ti plus 1 minus T times J in the ring where I've now adjoined a new variable T. And K is generated by T times F1 up to T times FR. And 1 minus T H1 up to 1 minus T HS. Step 2 is to, I guess, fix a monomial order that eliminates T. Say less than. We'll compute a Grosvenor basis G, G1 up to GL for K, this ideal we defined up here. And then we just do normal elimination. So we eliminate for K with respect to my order. And we eliminate T by saying that I intersect J is going to be generated by the GI in G such that T does not appear in GI. So
And note that that is going to be a Grosvenor basis of I intersect J as well.
with respect to the order that is induced.
But actually, that if you choose the T to eliminate T and be any order you want, next one, next n. If that, so. Pretty good. Is that
How do you know you have compensation?
oh, we have, we're right now we're black boxing the Grosvenor basis computation. We sort of said how to do it. You take all the S pairs, you take each S polynomial S pair and you reduce it using the division algorithm. And if you get non-zero, you add it into the thing. Otherwise, if you get zero, you ignore it. And you do go through all pairs, and then that has to stop, and it gives you the Grosvenor basis.
Okay, and so the order you pick, it's the T bigger than the variables.
Yeah, T is greater than x1, is greater than what, I mean, so T is the largest variable, and if I have T to the A times some monomial in x's, and I have T to the B times some monomial in x's, you first look at A and B, and only if they're equal do you ever go on and look at the rest.
Is the only order we know from the discussions in this class that work as an elimination order basically Lex orders? Because we could do something like a weight order where we weight
So there's a
P.
weight order, there's a Lex order, there's a product order.
Okay.
These are all different, actually.
Yes, but
Yeah.
for the context of this class, we've just talked about Lex, right?
On the homework, I mentioned some other ones.
Okay.
But, yeah.
Okay.
Should we leave it at that for the moment, or and then we can do some of the others later? You should think about The other ones are important.
Mhm.
And so maybe we should do at least one more of them, but I think probably it would be nice to. Okay, so thanks, Mike. Okay, so but this is the kind of, in fact, this is exactly the thing that happens in lots of different situations. You add a variable, you somehow make a new ideal inside of that. You intersect it with that by doing a Grosvenor basis, and then you just pop out the answer. So it's a good sort of general template for doing a bunch of these things.
If it's not too much trouble, you actually pick out a small line J.
Sure. I don't know, a minute or something. Okay, actually, that's a good point. It is really good to see an example. Okay, wait, I have to get on Zoom here. Oops, how do I have to go find the Zoom link again. Where is the Zoom link? It's right somewhere along here. Here it is. Okay. Oops, and I'm off of audio on this. People can still hear me online, is that right?
Yep, that's right.
Okay, good. Okay, so we're going to do an example. So let's what would be a good example to take? So I'm going to do an example of intersection, and maybe we'll do another one too while we're at it, just to sort of see how it goes. So I'm going to do the following. Let's take maybe take the twisted cubic and the rational quartic and intersect those, or is that's probably too big, but to see. But here I'll take a ring ZZ mod 101 of A dot dot D, 4 variables. I think that's enough. We'll let S be the polynomial ring where we add a new variable and we do a monomial order gets to be, say, Lex. Okay. So those are going to be my 2 rings, R and S. And now I'm going to take 2 ideals inside of R. Yes. So in fact, if I do T plus A plus B plus C plus D, I get that's in order. So T is the largest monomial. So it displays things in the order of that. Okay, so now let's take an ideal. How about I is going to be ideal? Let's just make it a monomial ideal first. How about A squared comma A times B comma B squared? Okay, that'll be one of them. And the other one we'll take to be this let's take it to be the twisted cubic curve. Oops, not call it I though. Let's call it J. Monomial ideal, not monomial ideal, monomial curve ideal. That's very different. Of R, and then do one. Let's do the twisted cubic. Okay, so this is 3 generated: C squared minus BD, BC minus AD, and B squared minus AC. Okay. And now I want to do an intersect of I and J. So the way I'm going to do it is I'm going to substitute I into the ring S, and I'm going to multiply that by T, and then I'm going to add that. That's an ideal. Let's make sure that's an ideal. Yeah.
So when you find I, you didn't specify the ring. So
Oh, actually, to tell you the truth, it is in that ring. I wanted to use R. I want to do it this way.
So is S fine, so
It would have put it in S. Okay, so I do this, and now T times that will be an ideal in S. Okay, and now I'm going to do 1 minus T times substitute J comma S. Okay, and let's call that K. So that's the ideal. So if I do net list of K underscore star, I get all these polynomials. It should be exactly so I have 3 generators for each one, so I should have 6 generators total, which I do. Okay. And now I do Grosvenor basis of K. Let's call that GB of K. Okay, there's 13 generators. let's make it, I'm gonna make it into an ideal just so it's a little easier to see. Or have an actual ideal. Okay. And now, again, if I do GBK underscore star,
Okay. Show all this. On this, but is it just sort of, it's not making any claim about the minimal, or anything, it's just like literally.
sorry, say it again and then I'll repeat what you're saying, because I've realized I've been bad about actually saying what it is. So yes.
So what, okay, so when you display K, you're like, I guess output 37,
Yeah, okay, here's K.
did a list, like, oh, okay, so is it, it's just sort of blindly combining all the generators?
That one is just a bunch of generators thrown together. That's all it is. Yeah.
It's not reduced, it's not- they're just a generator.
Yeah.
Okay.
Okay, so then what you do is I want the ones whose lead term doesn't involve T. So in fact, what I'm going to do is I'm going to select GBK underscore star, and for each polynomial, I'm going to take the lead term of F. Actually, let's just so I'm going to say member of T, comma, the support of that. Okay, the support of it will be the variables, T, A, and whatever. And I want the ones where T is in there, but actually I want the ones where it's not in there. So I'm going to say not a member. Okay. And that's what I get. I get a whole bunch of polynomials. So actually, if I do ideal of this, I have it's hard to see it. I'd better not do that. I have a way of doing it quick, but I didn't, it's not in the system. List OO is the last thing, underscore star. So it's 5 generated ideal now. Okay. Kind of interesting. It looks like 4 cubics and 1 quartic. Okay. If we look at the Gribner basis, if I do the same thing, I take GBK underscore star, and this is my favorite way of looking at these things. I just look at this and notice, because it's an elimination order, so those 4 don't involve it. This one doesn't involve it. But now if they involve it, it has to be the lead in the lead term. So TC fourth, it has a T in it. I don't want those. And so when I intersect with K of T, away from K of T, so K of the other variables, all of those guys go away. They all have T's in them. And so then I'm just left with these other polynomials, and that's the intersection. So in fact, if I type intersection of I comma j, oops, it's intersect. And I get that ideal. And it's not doing it that way, but that's that's one of the ways it could do it. Yeah.
If you wanted to intersect 3 ideals, could you do the same thing except use T times the first one plus T, 1 minus T times the second one plus 2 minus T times the third one? Or could you have to do like
I think
1 at a time?
so. So the question is, what if you want to intersect 3 things? And this actually does come up. Oftentimes, if you're interested in ideals of points, you might need 12 points, and then you need to find the intersection of all of them. So so you could do it 2 at a time and keep adding it in, or you could make a tree of it, or it's a little interesting which way will be the best to do it. But the suggested was, suppose I take three of them, I, J, and K. I could do T times I could do S times J, and I could do 1 minus T minus S times K, or something like that. And then I think that will give me, and then I have to eliminate 2 variables. To eliminate, it's a little trickier to use just 1 variable to eliminate in that case. I think you can maybe do it, but it turns out to be computationally more complicated. Anyway, so this is so in Macaulay 2, you tend not to have to actually do this by hand, but you can do the Gribner basis, just look through the ones that aren't there and stuff like that, and get it. Any other questions about that? Does that answer your question roughly, or okay? So I am now going to cut this for the time being. And so now I think what would be good is to try to do a couple of the problems on here. Now, let me see which ones we have. We have the three different ideals here. I suggest trying using the SIS for starters to compute the graded resolution, or I didn't talk about graded, just compute a free resolution of these things. They will be graded as it turns out, and then find the modules X, just see what they look like. Maybe you can do annihilator of it. ANN stands for annihilator, and you can also use the Hilbert. What time is it? I would like to show you how to compute from the Hilbert from the free resolution, the Hilbert polynomial, Hilbert series that we did before. Maybe I'll do that first, and then we'll do this. But because then you'll have the stuff to play around with all of this, and at least the first couple problems. Okay. Okay, so I'm going to start over here. Can you see me? Yes. Okay, good. So there were a couple of different things about this. So we sort of said that you could do the X modules. Well, we didn't say just sort of. We said you could do it. Okay. But I have two notes that I would like to do first, and then yeah. As usual, I'm going a little slower than I had in my notes. So some notes. Okay, we're going to do this for a few minutes, and then we'll do the project in fun time. Okay, so the first one is how to compute these. How to compute SIS modulo lift and image of F is contain question mark and image of G. Okay, these are the four things, and the answer is to compute Grobner bases. However, we need Grobner bases in R to the A. We need submodules as opposed to ideals. For now, we're not going to talk about that in class. You should be able to take the Grobner basis method and the stuff we've done for ideals and extend it yourself. But if you don't want to do that, you can so try this yourself. Or you can look in Eisenbud. Oh shoot, I didn't write down the location. What's the chapter in Eisenbud? It's 15 or 16 or something like that. Chapter in Eisenbud's commutative algebra book, I think it's chapter 15. He goes through Grobner bases for modules right off out of the box. So you can look at the definition of monomial order for modules and things. I think the Cox, Little, and O'Shea in the using algebraic geometry book, that's the second one. I think it's called using algebraic geometry. They have a section on computing Grobner bases over this. And one that's a little gentler than some of these things is Adams and Lustenau. And I had written down where they were exactly in these things, but I don't have it on my notes here. So Adams Lustenau has a book on Grobner bases, and they have a section on this. And it kind of gives you a gentle thing about modules and the whole bit, but then it eventually gets to Grobner bases of these things. Whereas this starts right off the bat at that. It doesn't even do it for ideals. Anyway, these are, this will give you, so once you have a Grobner basis of that, then this is just division algorithm. Keeping track of what's being divided by. And same with this. So these are both division algorithms. We're using a Grobner basis. of image of G. Okay, these two are use Gröbner basis to compute syzygies. You have to think a little bit about it. That's exactly what this one is. Just no change at all. This one, what you do is you do a Gröbner basis of the whole thing, but you keep track of. There's some tricks. You can just use sys and then grab the answer. That's one way to do it. But there are a couple of tricks to make it a little faster. So there's that. So that's notes. This is one. The second note is about gradedness. And this one is important because a large amount of how to use a lot of this stuff is for graded modules and homogeneous ideals and things like that. And that's where you get a lot of really good information. So I think it's worth saying something about that. So 2, if R to the A, R to the B, and R to the C, those are the ones we had above, are graded free modules. What does that mean to be graded free? Free means it's this, but it has now a grading on it. So i.e. F is equal to the direct sum of R with some twists that we had defined earlier, minus D, I say, from I equals 1 to A. This is like R to the A, but you're given degree, each of the A generators, you're giving degree, the ith generator you're giving DI is its degree. So if all of these are like this, and F from this free module, I'm going to write it as R to the B to R to the A, but really I'm thinking of it as I've given gradings to these things. And G is from R to the C to the R to the A. If these are graded of degree 0. What does it mean to be graded of degree 0? I think we mentioned that last time. What it means is that if I have a homogeneous vector of polynomials here, and I take f of it, I get a homogeneous vector of polynomials of the same degree over here. So the degree 0 means that you don't change the degree. You add the answer gets changed by degree 0, which means it's the same degree. So if these are the case, then in Macaulay 2, the sys and modulo, all of this stuff, the answer, we want to require it to be homogeneous. So what does that mean? That means that when I take sys, instead of getting some combination of things in all sorts of different degrees, every single vector has a fixed degree and is a homogeneous element, and that like the image of sys of f is minimally generated by the columns. In other words, you don't have you don't have extra stuff that you don't need. Okay, so if you do this, then all of the things will stay homogeneous and graded, and everything is great. Okay. So what I wanted to do actually, as far as this goes, is that, yeah, let me actually do one thing, and then this, I want to say how to get the Hilbert function of these and what it means a little bit. So we already showed how to get Hilbert functions of ideals and things like this. So here's a different way of doing it. So I'm going to suppose M is a finitely generated graded R module. Just in my usual grading, the variables have degree 1, the whole bit. Okay, and then what we have here is that so this is the direct sum over MD for D and Z or something like that. It's finitely generated though, so you can't go negative all as far as you want. You know, there will be some minimal degree D in there if a sense is finally generated, okay? And so the Hilbert series of M is, so this, like, an example is just M is equal to R mod I, where I is homogeneous. If that's totally fine one to deal with. These are the main ones, but there are going to be other ones that we're going to talk about too. So in fact, in the project, the X modules and things like that. So this thing here is going to be the sum over D and Z of this dimension of MD. Remember, this is now a vector space over the base field K times T to the D. This is the generating function, and before we had defined it for M equals R mod I. Okay. Now the theory, it gives you that this is equal to some polynomial P of T over 1 minus T of the number of variables plus 1, and then you can factor out a bunch of 1 minus T's, and you get another polynomial over 1 minus T to the R plus 1, where Q of 1 is not equal to 0. So you can't factor out any more 1 minus T's out of Q. Okay, so this is always the case. This implies, okay, so when you have something like this thing, this implies that the there exists this polynomial, there exists a polynomial, let's call it P, I don't know if that's what I really want to call it, P sub M of Z, such that for Z, an integer large enough, and Z, oops, the dimension of M in degree Z is equal to P of Z. So all of these things are taking the value of polynomial, and this is called the Hilbert polynomial. And you can see this directly if you have any rational function like this. This is going to be the case. And from this thing, you can figure out what that polynomial looks like. And it's going to look like the following. It's going to look like some constant E times, with this R here, times Z to the R divided by R factorial plus lower terms in Z. Okay, so it's a polynomial in Z, and there are no higher ones. And then these numbers, R is equal to the projective dimension of M. Okay, if R mod I, if it's homogeneous, this is going to be the dimension of the zero set of I in projective space. Okay, that's R. And E is what's called the degree of M, or the multiplicity of M. Depends on if you're more algebraic or geometric, which one you like. And that's it. The other lower terms are really good information too, but we don't need to worry about that right now. Okay, so this is the situation. And now here's the cool thing, is that if you have a free resolution, you get all this for free. Relatively for free. Okay, so if I have a free resolution of M, F0, F1, and this keeps going, let's suppose it finishes at some step little f sub little m. Okay, remember, if it's R mod I, it's just exactly what we've done. Otherwise, it's instead of starting with a matrix with one row, you're starting with some other matrix here. And so if this is a graded resolution, which will be the case if you use those sys commands or in Macaulay 2 or whatever, is a graded resolution. So all Fi are graded, and all maps have degree 0. Just like I said, are homogeneous and have degree 0, or are graded and have degree 0. Then what do we know? Okay, each of these things has grading. So then if you just look at it, what do you get? You get, take the degree D part of this. since everything in degree D is going to degree D, that part of it is exact. So you get 0 mapping to MD. This is a vector space. F0 in degree D is a vector space. F1 in degree D is a vector space, all the way to Fm in degree D is a vector space. Exact sequences of vector spaces. I've tried teaching this at the undergraduate level. It doesn't go over very well usually, but it's pretty easy, right? So what you know is that the alternating, this is exact. This was exact, therefore this one is exact for every D, for any D or all D. And consequently, since these are all finite dimensional vector spaces, the alternating sum of all the dimensions is 0. So then, therefore, we get that the dimension of MD is equal to the sum of -1 to the I times Fi in degree D. No, sorry, dimension of that. Of I in degree D. Okay. That's going to be the case for this is I equals 0 to M. And therefore, the Hilbert series of M is equal to the sum of -1 to the I times the Hilbert series of each of the terms, F sub I. So this is of T, this is of T, and this is I equals 0 to M. So this is really cool because what are the Hilbert functions of these guys? But note, if I take F is equal to the direct sum of a whole bunch of, say it's minus, I guess, DIs, I equals 1 to some number, A, whatever. What is the Hilbert series of this? The Hilbert series of F is it's a direct sum, so it's going to be the Hilbert series of R of minus D1 plus ... plus the Hilbert series of R of minus DA. Okay, it's just it's in one of these spots, so that sums them all up. But what are these things? This is this. I think we did this one. That is T to the D1 over 1 minus T to the N plus 1 plus ... plus T to the DA over 1 minus T to the N plus 1. This is exactly that's exactly the P of T over that. So if you know the degrees of all the entries in here, you can just write it down with no effort. And that's what one of the things to do in those 3 examples I gave. There's the twisted cubic, the rational quartic, and then some monomial ideal. So we'd like you to take a look at those, look at the X, and sort of say things. What you will not necessarily notice right off the bat is that you are staring at some really good theorems about these things when you do it. And almost all of everything that you write down about it, we can hopefully try to make into something general and good. Any questions?
We don't need minimality for resolution?
No. What's going to happen is if it's not minimal, because of the alternating sum, if you have an extra one here, you have an extra one later, and it'll cancel out. So, and you can sort of see it really doesn't matter. I mean, if this is exact, then this is certainly exact, whether it's minimal or not. Yeah. So, typically you do it on a minimal one, but you don't have to.
Is this how Macaulay 2 does it?
No. Macaulay 2 does it using the initial ideal, using the Grobner basis of modules. And then what it does is it calculates it combinatorially that way. But on the other hand, if you have the Betty table, so all these degrees here is the Betty table information that we had before. If you have that, then it will compute it that way. So you can actually say, I think you can do Hilbert series of a Betty table. I think you can do that, and it will give it to you. Actually, I'm not 100% sure that works. We'll have to try it. Okay, so anyway, what I recommend is it's 12:10 now. I recommend that actually maybe we do the rest of the time on these examples. Maybe we get together in the last 10 or 15 minutes and then we can sort of say something about those examples. So why don't we go for about 30 minutes would be until 12:40. Let's do a half hour of it, and then we'll we'll get together towards the end of that. Okay, so
Mike,
work together with people. Yep.
just in that
question?
very last thing you wrote on the board directly behind you, F equals big O plus. What are the indices going from?
So are
I
you talking
equals
about right
1.
here?
Indeed, yeah.
So F is equal to the direct sum from
Yep.
I equals 1 to A
A.
of
Gotcha.
R twisted by minus D sub I. So in other words, I just have A summands, so it's an R to the A. And I give each generator is going to have degrees D1, then D2, and so on up to DA.
Gotcha.
And then the Hilbert function just splits up as a sum, and then the rest is history, as they say.
And then what about the exponents of the denominators below that? 1 minus t to
right
the
here. Okay, so this is a t to the, when you shift it, it's just this t to the d1 is just shifting over the whole thing. Because and this is the Hilbert function of R is 1 over 1 minus t to the n plus 1. So that all
it's
of these are
all
1
n
minus
plus 1.
t to the quantity n plus 1. So they're all the same. And really, because that's all the same, you're just taking all of the things that appear up here and taking a sum of them. But of course, you have it's a sum, but it's an alternating sum from in after for each one. But it's worthwhile to sort of whenever you see a Betty table to actually be able to just immediately go from that to seeing what the possible Hilbert polynomial is. Actually Hilbert function is a worthwhile thing if you haven't done that at all. If you have done it, then you won't need to do it again. But yep.
Going back up here, when we wrote P of t over 1 minus t to the n plus 1
Yes.
equals Q equals the Hilbert series. Does this work with non-standard grading?
Oh, so here's the question. So up here I had P of t over 1 minus t to the n plus 1 equals Q of t over 1 minus t to the r plus 1. Does it work for non-standard gradings? In other words, where the degrees of the variables are not all 1? And the answer is not exactly. So what it is true is that instead of 1 minus t to the n plus 1, you have the product of 1 minus t to the degree of each variable. So that's okay. And you can divide out by a bunch of what, but then going here is you can look at still what the power of it is, but you're not going to get this nice reduction like that.
But it's still rational.
Still rational. That's right. There are things you can say though. I mean, it's just needs a little bit more. Okay, any other questions? Do you want to work on some of those problems now? Do people have computers here that they can play around with? The first one I had doesn't have any. It's just basically going through and doing it on a simple example, I think. That one was suggested to go through by hand and do those. It's not a bad way to start if you have never done these before. But if you want to do the Macaulay 2 ones, you can. Okay, so we'll get back together at about say 12:45. So in about a little more, about a half hour from now. I'm going to take this off here. Yep.
I'm just starting to do problem 2, and I'm trying to do A. How do you? So I managed to initialize this stuff. I'm really quite new to the whole idea.
Yeah, it's cool.
How do you get a free resolution of quotient ideal?
Okay, so first of all, you should think of that as R to the 1 mod I. So if you want a free resolution of it, you have two ways. You can do res of parentheses R up arrow 1 mod I, or you can do res of I. It will give you the resolution of R1.
Okay, cool.
So it's one of those things that, you know, if you give it an ideal, it treats it differently than if you just give it a mod.
Cool.
I used to hate that, but I've embraced it since then.
So we've already done res of I, but then if we try R to the 1. So yeah, that should go, right? There we go. Oh, yeah, that's about it. And it's just okay. Yeah. Very cool. Now that was A done. Now find the modules.
I don't know how to use that.
So
Let's go.
we did it, if you just type, it's probably good to do it by hand.
Yeah.
The first time, because it's too slick to just type in X upper or
Yeah,
whatever of that. So I recommend. Do it a little bit by hand. Sure.
What is the dimension and what is the degree?
Dimension is going, if this is R mod I here, the dimension is the R. Okay, which is the same as the R up there.
And apply.
Okay,
Okay.
and the degree is the E.
Degree is the okay.
Thank you.
Yep.
And then flipping carrots, and then you take the kernel mod image.
This also gives you arithmetic genus and section genus and stuff like that, but that's for later.
So you talk about X, but so it makes sense to compute X1 and X0. But
X0, X1, X2, all the way up,
So
yeah.
X0, you had the delta 1, so is this delta 0 then? Makes the map.
There is no delta zero.
Ah.
So then, the typical way you do it is you ignore this
Ignore that.
and that you transpose all these things.
Okay,
And then you kernel mod image, but the image will be zero here.
okay.
So that's a good point. I don't think I mentioned that.
Because you said xi is kernel
just keep
delta
that.
I, right?
Kernel of delta I plus one.
I plus 1, I see.
Transpose.
Transpose.
Mod the
I-
image of delta I
I see.
transpose.
But
But
you-
if they're out of range, if they're not one of the ones you have, there's a
Yeah.
zero.
Yeah, I see. So image of delta 0. We
There
don't-
is no delta
there is
zero.
no delta 0.
So the image of delta zero is zero.
Yeah,
So the very first step, the X zero is just gonna be you flip the thing around.
just the kernel.
You just take the
Goes up.
kernel the opposite way.
So Macaulay two, when you compute the free resolution, it just doesn't output that at all, it just does that.
That's exactly right. So the free resolution is the part that's free.
Right, okay, that's fair. Makes sense.
Now, A. Compute the graded free resolution of R, which got the computer to do that. That's
Yeah.
really what we did today.
Yeah.
And it's made really helpful with this computer. In Macaulay two, I know you think there's some stuff to deal with blocks, right?
Yes.
It's like, what was that, calculus package, you can do a lot of them. Second theorem, why is there no zero? You know, if there's either ability to, it's just not. But it's a map.
I mean, you can always just make it. It's trivial now.
Dog, I don't even know.
So you want, you want to compute the resolution of God, yeah, with using blocks.
Of a rational. So that, if I have a rational map, you just all. Projected base.
So if I have a map, so what is a rational map? On the projected space? You have a map in there, subrise inside of it.
Zero. Like just a rational map, PM to be a given.
And then you're thinking of blowing up the images, or the indeterminate nodes.
Because you want to.
Yeah, got it. So you can certainly, okay, so first of all, it is not actually
Got
as such.
Zero map, right?
It is implemented singular,
And we've got.
but the answer comes out to be very hard. Because it doesn't look, it doesn't package, and you get 100 packages, it's very hard. And I would really like to have that in the code too,
And then.
but I don't know how to do it in a way.
Image of this map is the ideal.
You know,
inside of that.
So you mean two different steps.
But I think in
Okay,
an
so
instance,
image of
you can
this
certainly
map.
look at this map.
This map.
Resolve
That ideal inside.
So.
Because
But also
this-
graph.
This is the action.
So I take something in our map and determinacy, and I just take. the
Is
graph of
is
it,
Armada.
Is
Of the part where it's
I living inside.
closure of that.
Yeah.
That will blow it up.
because I is an ideal, at least inside of that. Right?
But all the.
So I is really in there. Being very single. What I'm saying is.
Yeah, so
actually I is
the real
being
problem with
there.
that is if you do things projectively.
And why is it being
projectively?
because
You keep adding
the,
products of projective. You're
columns of this matrix.
So,
are precisely
so that's one of the
So
advantages.
the image of this map will actually
Join up.
say every.
So like,
If I
for
take
instance,
something
if I
here
have
and I part of this map, it goes to, by definition, something in your combination range, that's what is the idea. That's right.
local,
That's right, yeah.
that makes still surface, so I think I can have a bunch of things that are all.
We've done that.
3 dimensions, you know, 2 dimensions. And then I can now have the new polynomial
We'll
defined.
try to follow the algorithm here.
And
Okay,
that
step
actually.
one was this. Step
That's not. So if you're interested, it'd be a great
taking
project.
care of.
And also would be, even to figure out, you know, the math.
Okay, step two. We want to
Alright.
apply on.
Yeah, I guess we might want to compute the other.
Always look for zero. Where are these other symbols?
Yeah, that's right. So there's a lot of resolution of singularities stuff that would be like.
Wait, so we're basically looking. And we stick in systems.
Well,
It's
so like,
on my
basically,
list of
I
things.
each step, I get this matrix.
Very long list.
So like
Like
essentially
this, maybe.
this matrix.
Yeah,
So
exactly.
it's- the
But
things
the
that get done.
big idea
things
of
that people
right is
say,
we're essentially approximating.
Because otherwise people aren't.
This is like an approximation. Yeah, so.
So it's done. Okay.
Here's the ideal, right? Like,
Anyone need any help or anything? Are you doing
they
that?
could look kind of the same, like maybe they're.
What?
Generating some kind of horizon. That doesn't mean the ideals are necessarily the same, but there could be like higher relations between with non-trivial higher relations between the generators, and that is really telling you how the structure of the deal works. So basically, start with your generators, and then what are the
Oh, a
relations
couple
with
weeks
those
ago?
generators? Well, that's what this makes, exactly, that's what this. That's what this makes.
Congratulations.
And then you
any
can
other
say,
steps?
what are the
These guys,
relations,
those-
exactly. And then say, what are
Oh,
the
yeah.
relations of this generator? Oh, there's no more, that's when it's solved.
Yeah, right, okay.
Okay.
That's the idea. So.
Wait, so then why do we do it? It's already calculated.
Yeah, no, we got this, so we're done, you're right,
That's
actually.
step two.
Yeah, no,
That
pre-resolution
was the
that's-
end of step one, so we already got that.
I mean, okay, so,
Okay.
you know, they,
And our apologies.
especially now with this,
The, all the,
you know, it was all done, it was never a computational thing. Always a abstract. It was only actually after the all programs.
So my understanding, what is it, you take this,
Anything
we'll go.
So,
And then solver that,
and they,
R
it's really.
star,
Cool.
R star, R star.
I was able to,
From the other way.
oh, so you're just like, you're just making it.
real life.
Understanding
as far
is that
as
we're
you can see
end up
what's really happening.
Zero,
Equation.
R one star,
Yeah.
and then R,
Yeah.
maybe a stupid way to do it, but this way. Two star.
I mean, I've heard it, but I could.
Oh, I see, you're making it.
That's right, and then we
It's,
go this way now.
Sort of alternate, yeah. What's the? To reform what to use.
Oh.
It's like Roger Penrose. So it turned out it's all praised in.
And now, what we do to get these guys is we take the transpose of these guys, and so this
Physics,
is now
it's called
X.
Feynman. And there's an analog.
Z, and then
They
different
evolve
weight. make
integrals
Z,
of complex functions.
So this is now a map. of shell models, or it makes sense, so this is a two line.
and
What
then
happens is
three.
Quotient.
So wait, I'm gonna say five ops.
Spaces.
Oh, awesome.
And so what, so that is done.
Dual.
So
This is a complex stuff.
Yeah. And I found
I think it just means.
counter
It's like,
to a certain
it's like almost exact.
Sure.
And
Yeah, well, I mean, the image is.
Yeah, exactly, yeah.
It's not exact.
Or
the
not
image would be
exact.
different, but okay,
in
so
some
now.
cases, you
Compute
could actually construct
X.
contours that these contours.
Well, where's the I?
What we're doing is at each step, we're taking a kernel of one, we're doing it each eye, yeah.
Oh, so it can be trivial here, and then non-trivial.
Exactly, yeah, yeah.
Cool.
Yeah.
Anyway,
So,
I figured them out.
Just for
So-
completion's sake, let's start.
I found
with
it.
the
So
So
it's
it's
conjecture.
0 through class. will
these
be
diagrams would only
kernel
one contour.
of
algebra.
this. Oh, I guess that's-
So
I
I
guess
thought,
that's trivial.
so I thought
So-
another example.
Yeah, I guess you can just start
So that was
with
one.
one. Yeah,
But
start
I,
with one.
when I can construct one of the cars. it's pretty clear. So, I never could construct. Equations. So,
And then we're defining this.
And
as-
it always, it's always in the back of my mind that I get screwed up. Yeah, maybe it's the wrong. But, you know, so that's why I'm interested in this computation.
So, yeah, that's
I'd
like
like
it
to
to be
see-
very, very related. to it. That would be
Okay.
very cool.
So let's do.
The thing is, in order to actually apply it, you have to.
One.
You basically have to.
R.
Kernel of the second map.
R.
have a-
So it's the kernel. So this is the first map. This is the second map. This is the third.
Yes.
Okay, so the kernel of the second map. equals
Common.
Sorry, I just wanted to double check
Divided up.
this, right? Because how could we
Simple.
define?
It's something like this, you know, that
No, it's not.
No, I think it's either off by one, right?
to be
Because
manifold.
F. Well, we don't even have an
then
R on
F
here.
zero.
R.
So
So
basically,
so I think you'd get a.
yeah, so
So we missed it.
Get a combinatorial explosion, so there's a high dimension, because this
this guy.
space was the minimal example.
F is gonna go.
Was-
F was our original map.
Product
Five,
of
six, first guy.
Three complex.
This guy is your R.
Three
And
spaces.
then,
complex.
yeah, so you would have an R mod I.
It's like 18 complex dimensions.
You would have an R mod I there.
So where's that here?
So like. do
No, I don't think so. I think this
Common
is
for-
R.
Yeah, no, that's.
There are, it's
that's
a possible.
R mod I and then.
If you can translate to that.
Wait, so then where's our R?
Yeah.
mod I?
You can actually.
The R mod, you would just.
So I
have
actually
another-
have seen that. I, in fact, I've been working.
It's kind of like whether you choose to write the R mod. You're just shifting the line.
But you have a map that are 907 three-dimensional space. And you can still figure out what the image is. So it's.
And so it would be like, there'd be two steps, like one would be
And
the
then-
topological aspect, reduce it to algebraic.
Yep.
and that actually
Yeah.
Applying some.
So there's another case,
R
that this happens a lot.
mod I.
It's in what's called intersection theory.
Mhm.
So where you.
And
where
then
you
what's
have
this?
Yeah, so now it's-
that's
that's the
question.
Why don't we write what this map
Intersection
is? Well, after you've gone through this,
I mean,
essentially
you can
you're
calculate
inside of
things
the
that
idea.
you never have any
You know,
chance.
for here, that's where your image is after that. So,
But the
I
image.
mean, the very fact that.
R2
they're
into
even-
R1.
well, yeah, the image is.
I guess
this guy.
It's oftentimes.
But because
they're
you want the
into
kernel to be
resolution.
contained inside of this thing, you're already living in I. This is,
Yeah.
this is the canonical surjection, right? So this is just, this is just the map, I mean, this map is just the canonical surjection, because it's taking anything R to R on I. So that will, so having that.
But it's everything, it's everything that's not in the kernel here. Or in the image here.
Well, it's taking everything in
Yeah,
R
right.
to R mod I.
So,
but
so.
That
this
map will
is,
agree, will be a complex
trans-
because of the fact that the
translate-
image of.
These are actually gonna be
is
R2s, not R minus.
Then that agrees with the kernel, like image being the kernel. property. So this map is
You
just.
can't actually have an R map.
Which is,
like.
Um,
not obvious.
This is, they literally call it the canonical surjection. It takes R, sorry. Takes
R minus.
takes R.
Sense.
This goes set.
Like if you want.
Yeah.
Canonical surjection.
Okay, so
That's
what
what
do we
that
write?
means. You don't need to write it.
So then, so E1 is degree 2 here,
Yeah.
maps to this, but if that were, so that's here to R. Oh, wait, is that where
We have R,
when the other way?
mod I.
Yeah.
Yeah, here you went, here, here the degree element is in degree 0, right? And if you map it here, there's no elements in degree 0.
Oh.
So I think when you dualize, oh, I should have said that, when you dualize.
I guess you can't really,
Because all.
you can't really write the, like, you're thinking of things as like, you know, R2, R3, like actually like real vector space. It makes sense to think of it as like.
So then, that's what's.
Wouldn't really make sense, right? It's not like, like the dimension is not really how it would say way. You're not moving from a two-dimensional space, but whatever, you know what I mean? Like, like, this is a, like a somehow different type of object than all these other operations. That's kind of the reason why you, I guess, would want right here. That's my,
Okay, hang on.
Like the idea.
Oh, sorry. So this is del.
Kernel,
Del One, this is two, this is del three, but and so then this is del.
Yeah, that's right.
This is del.
Oh, you're doing the, yeah, I didn't think I understood.
Well, actually, I wouldn't want to.
So that's actually now.
You want the kernel to be.
Okay,
Generated
so
by
we're doing
that.
X, so it's the
And the
kernel
image
of
is
this.
So what is that?
This divided. So I'm gonna write it out as curve.
Yeah, because your math's not hard, the math is just multiply by Z.
I guess.
Well, no, actually, it's
It's
a
right.
generator of one kernel. And then the image is one image, so it's gonna be one the sub module of that.
Yeah.
That's gonna, because it's generated of one, it's gonna
One,
be.
so it's-
R.
What things are gonna
go
So I don't really know.
The degrees will end up being, so here, what's the degree in the spectrum?
Okay, so if you,
So it.
I don't know if I'm reading
The
it,
generator here would be
but we
negative
wanna
two.
feed into.
Okay, so I don't know
Yeah,
how
but
far
if
it's.
I add
So
one to it,
at the
then
very
it's
least,
gonna be
feed into it, y,
So that'll be like an R.
now we'll get that's zero.
But maybe, but you can figure that out.
Yes, but I think it can't look like that because the map is going to be you're applying this.
Those both look like
Z,
it's-
Y, which is a by one matrix. Like you'd be applying it exactly something like that. So it's Y, Z. Likewise, any,
The situation for time, maybe it isn't. Agree, but.
I guess any.
Sort of.
Yes, yes.
Then that vector.
And in fact, any R linear combination.
Yes.
Yeah. Alone.
Right.
So I think that's.
Okay, I guess that doesn't mean that
Columns.
the last map didn't do well. But.
Because we multiply it by, we multiply both top and bottom by X, Y, Z, or any of them, such, and it's.
So.
I don't.
It's synergy.
I don't know if it's like.
So,
Yeah.
my guess is that if
like-
they're using their mixed derivatives.
No, for X.
Okay.
Oh, X one.
So-
This
That would be, by the way,
Like-
I don't know if you're interested.
Yeah.
Ideal generator,
Yeah.
by, what I have at Y, and Z. Cool. And then in, here, in the image,
I think it's online.
this guy,
Right, so what happens after you apply that map?
so we're hitting it with our arbitrary shift.
Yeah.
I think it's one object.
It was just a one.
And it turns into R linear combinations of this.
Yeah.
No, because.
Because you're turning a one-dimensional line into
Oh, and this is the negative. And so you get, that's just R linear combinations of X, Y, X, Z.
Yeah. Yeah.
Right?
Just line single.
I mean, sometimes you can, but you have to be careful.
Aha.
3 by 1 by
But you
1.
notice that what you get left with here, so. This down here is just this multiplied
But
by X.
even in that, I mean.
Yeah.
So what we have is the ideal
Yeah.
generated by,
Actually, I was gonna.
divided out by the ideal generated by an element times the thing.
Try to create. One way to come to.
So what is that one of those? So it does make sense that. Yeah, definitely this is. That makes sense.
But as far as our one, I have to think about which is.
So
What? Yeah, but I don't know if you can actually just immediately get.
They're gonna look like. Well, okay, so we know that anytime you have an X multiple of this guy,
yeah.
so, okay, so everything looks like an R multiple of this, so we can sort of ignore what this is.
Yeah, I guess I'm not
And
really sure with the
instead,
presentation.
anytime you're multiplied by an X, you go to 0.
Yeah.
And anytime you're multiplied by anything else, you don't. So it's gonna look like the ideal generated by.
You mean like, you wanna find equations that cartoons? Yeah.
Except I don't actually. I mean, that's the idea. I guess you have to.
Right.
But I guess really, what are the concepts like? The elements of that.
Yeah.
These things. This is a quotient object. So things like our space looks like this, and then things from the top. The things from the top are gonna look like X. Oops. X, Z.
So I don't
And
really know.
then multiples of that, but this thing. Lives in. R. R2. So this is gonna look like an R2 is a 3 module on an F. R is okay, alright, so okay, so this is like all times. Like formally within a sense like, and then does it make sense that that's basically this thing? Is that kind of, yeah? Because when would two of these guys be equal? When the difference lies in this thing. Let's say there's a difference for y in this thing.
But that would be, yeah, that direction.
X, this is X, Y, X, Z. So we're expecting. Are we expecting Y, Z, or are we expecting X?
Okay, yeah.
Well,
I'm gonna say no.
anytime you multiply it, so this looks like.
Or people do it, okay?
Right? Okay, so this is all our multiples of y z. This is all x.
Oh, yeah, okay.
Is all our
We
multiples
might
of
not
y z.
quite dive in to really.
Okay. So
But it's.
these guys get mapped to zero. So if you
So
obtain an x,
I would guess.
you're an r multiple of y z where you the r multiple contains an x. You're in zero. So everything else that gets left over is the y z
I might, I
only.
might change. the
Y z. And so it's just gonna be the idea generated by one.
Although one good, one.
All
fun
polynomial
thing about
multiples
Is this
of
thing about taking.
y and z times y z.
Four random, not random, it's four, but homogeneous quadratic polynomials. What are the kind of Venn diagram?
Yeah, I guess it was confused how the.
Can we answer your question?
Sorry, I think you're right. I don't know how to like one by hand.
Yep.
So the first X module is the kernel of the Del two transpose of the image of Del one transpose.
Which is?
Is this the right way?
Yeah, that's what I was
speaking of those.
No.
Okay.
So, okay, so, first of all, what is, so where's your map here? So X1 is being computed here, right? So you're taking the kernel of the transpose of this. So that is a single. Which is X, Y, Z or something. Yeah, okay. And then this one is the image of this, and that's a single element also. So you have a single element. It's a vector and times the whole ring, modulo the ring times some other vector. So that's not gonna have two generators.
Okay.
It's gonna just have, it's just generated by one element, which is that Z, Y, L, Y, Z. And then it's a question of what is not, so that maps onto this thing. So I have a map from the ring to this module, by mapping one to that vector. The vectors, and,
It's y z. Yeah.
Is this like correct, like written, or is it writing this properly? Like, is this?
there's only one thing in the in the image of this, I think.
It's the vector.
Oh, I see, that's an X, Y, yeah,
Yeah.
but that's not
That's
equal
not-
to Y, Z.
So.
What it is it's singly generated.
Yep.
So as a module, it's gonna be isomorphic to R modulo something. So if I take R and I map it to this module, and I send in one to that vector. Then I look at that mapping onto that, right? No matter how I do it, I will be able to get it. And then if I take the kernel of it, then the R mod, whatever the kernel, which is gonna be an ideal, is gonna be isomorphic to the image. Right, so it's gonna be of the form R mod something.
Oh, okay.
And it's not by two generators, either. Right. But so we'd have to check that.
So like, what should the presentation be looking like when you actually write down the general? What do you want it to?
For this one, it should be just R mod, some matrix, okay, or some one row matrix.
Sure.
Like, in this case, it'll probably be a single.
Right.
And, but in usual, it's not, so it's, and this is a simple case, it's usually more has more generators.
Right, okay. But like the general idea is like you get to this, like just like working formally from it, you'll get to this step and then you'll say, okay, well, this is actually isomorphic to something.
That's right. So now if you want it, so that's for the X, I mean, typically, sometimes you want it to be related to things you started with. But X is a little hard to do that.
Right.
I mean, actually. Did I actually say anything about? Yeah, no, but later, the trouble is we haven't quite gotten where that's gonna be. Yet.
That's what I was, trying to get
So
at.
this is not the
I
same
think
thing as Y.
the rendering on
That's not.
this.
That's the thing that I need to.
And then I
yeah.
don't know how.
This
to
makes a lot more sense.
Yeah.
do that.
Because we're just saying, okay, well,
Right.
anytime you
So-
multiply by X,
So I was
you can multiply this vector by
This is
anything in
the
R
model
as long as it
that-
doesn't contain X.
So
Yeah,
if
actually,
R
I think
maps
because in general, the way that
module,
you, this quotient
by
kind of
taking
thinking
that
works is
one
like, if I
and
have like,
that out,
if I have like,
that's
A,
a
B,
subject.
C, whatever. And then I quotient out by like,
So
B, C,
kernel.
D, like,
Anytime you have, let's say,
roughly speaking, this is like,
it's just
A,
You wanna figure out.
A and D, or A and D.
That could be all-
but thinking about it as.
R modulus.
So,
Is a more accurate.
yeah, exactly, yeah.
Um,
So you're removing, you're
Because the
removing,
quotients create cosets, whereas this is creating elements.
yeah, so really, exactly, so this really makes, or like, I guess, maybe another way. It's, say it.
Oh, that's good.
Yeah.
And that's it.
Yeah.
That's it. So X2 is also gonna be. Right? Is that right?
Yeah, something like that.
Because everything maps to 0, so the kernel is, whoa, hang on. The kernel is everything, but the image is not everything. Okay, so let's actually, let's work it out.
So slow.
You are not slow. I don't know what you're.
I am just, yeah, I don't know what I'm doing.
You are not slow.
No, it's just in the conferences. Yeah, right.
Interesting.
Okay, kernel D3 or del 3. Mod image. of del 3. Okay, so what is the image of del 3? It's everything. Oh, wait, no. Kernel of del 3 is
Kernel.
so it's just R. Modded out by, oh, okay, so she's.
Yeah.
Okay, so it is gonna be sort of trivial, but it's trivial since it's one step back. Okay, so the image now of everything in here is going to look like, okay, so you eat. Two copies of R, multiply the first one by minus Z, multiply the second one by Y, and then add them together. So it's just gonna look like. Oh, okay, so that makes sense. It's gonna look like R. And this. Yeah, right?
Yeah. Yeah, that makes, because all elements will look,
R multiples of
yeah,
minus Z.
exactly, all elements will look like something times negative Z plus something times one. Yeah, that's exactly what that is.
Okay.
Yeah, okay.
Makes sense. And then that's it, everything else is good.
Yeah.
Well,
Except for this.
Should we talk about some of these things together yet, or do you want to wait and a few more minutes? So which ones would you like to so are you all online, or anyone who's still there? So should we go through any of these problems? Like, did people do okay on the by hand problem?
Mike, can I
which
ask a
was-
question first?
Sure.
In the, I guess our top right board, the Hilbert polynomial there, does that say R is the projective dimension of M?
So when I say projective dimension, I don't mean that's not correct. It's the dimension projectively of the
Okay,
model.
so like cruel dimension, like,
Yeah, so it's the Cornell dimension of M is R plus 1.
sure,
Okay.
okay.
And then as like the annihilator of it in projective space will have dimension R.
I see, that makes more sense, thank you.
Sorry, that was a really bad turn of phrase I put in there, because it's not the projective dimension at all. So any other questions before we get started? When I say we get started, we have 15 minutes left. So getting started is a little but I thought maybe we could at least go through and do some of these things. If you want, we could do it the computer ones, or we could do the hand ones. What would be most useful to people? Hand one. It's interesting. You get it's not that you get rusty. I actually, the number of computations I did by hand in writing this whole thing was just phenomenally large. I mean, really, yeah, gnarly ones sometimes too. But anyway, okay, so let's take a look and see what we have here. So the idea is we have this ideal I, which is generated by two elements, x, y, and x, z, in three variables. Yeah, I'll just write R. And then we have a handful of things we want to do with it. First is find the graded free resolution. So here it is, R mod I, R0, R. What's the next step going to be? Yeah, R squared, but also since they're degree 2, it would be -2 and then 2 of those guys. Okay, so this says that it's R squared, but they both have degree 2. Okay, and this is the matrix XY, XZ. So the first generator here goes to XY and the second generator goes to XZ. Okay, now what's the kernel of this? I think we did that sort of before, but right. So certainly this and -y, this is one of the elements of the kernel, right? But in fact, if you think of it, because it's only 2 generators in a polynomial ring, if I take some polynomial times this plus some polynomial times that equals 0, you can factor out the x. And so that polynomial has to have a factor of z in it. And this one has to have a factor of y, and that's it. That gives us any multiple of this. So this is it. And now what's the degree on the last part here? It's -3, right? Because this is this element here, this is really z times e1 minus y times e2, and e1 and e2 in this thing, if they're the generators, they have degrees 2. So this has degree 3, and so you need a -3 here to map to it. Okay, and then that's the last one. So this is the free resolution. Okay, even for monomial ideals, actually saying what the minimal free resolution is like a non-trivial process. And there's lots known about it, and it's kind of has a really cool story, in fact. But we're not doing that right now. So now we're going to go. That was part A. Part B is to find the modules, the X modules. Okay. So what we do is we take this part of it, this is the resolution here, and we ignore this and we dualize it. I kind of didn't mention that before, but I mentioned to some people in break. So we take R and we dualize is pretty easy. It just transposes everything. Okay, and that's a 0 here. We ignore the R mod I. And now what's this one become? It's kind of interesting. If you want the graded thing, this is going to be an R2. But it's going to be where the generators here are in degree 2, but the generators of the dual then are in degree -2. That needs some proof, but that's of 2. Okay. And then that maps to this one is going to be R of 3. So it just negates the numbers. Okay. You can sort of see that that's going to be the case. Well, but anyway, let's not go there. So let's leave it at this. Now, what is this matrix? This is it goes from a 2 to a 1. So it's the transpose of this, right? Z minus Y or Z minus Y. Okay. And this is it. So it's really just taking this and transposing all the matrices, and of course the directions go the other way. Now here, if you take kernel mod image everywhere along here, except here, kernel mod image here will be R mod I, but all of the others will be 0. And here, what are the kernel mod images? So this is going to be X0 is kernel mod image computed here, right? Now you might not, if you're not that familiar with the whole homological algebra game, this turns out to be Hom of R mod I into R. But there are no homomorphisms from R mod I into R. So this should be 0. But that would be the kernel of this. Image is 0. What is the kernel of it though? Well, that would be a polynomial f such that xyf and xzf are both 0. There are none other than 0. So in fact, this is equal to 0. Okay. Then we have x1 is computed here. So this is x1 of R mod I into R. And this is what various people were saying, so that you want the kernel of this thing, which is 1 generated. And what is it generated by? It's just, what is it, YZ? And you take the submodule of R2, that's the kernel of that. But we're modding out by the image, and the image is just the image of this one element here. So that's a submodule generated by XY and XZ. Okay. So now that is a module, but we want to write it in a nicer way. So we want to write it as maybe a free module modulo something like so this has 1 generator to it, or it could have 0 generators if that is 0 if you've modded out by it, but has no more than 1 generator to it. So what I can do is I know that I can be able to write this. I can do R and map it, R mapping to this to R2, mapping to this element here. And now I have to just calculate what the kernel is. So what is this module isomorphic to? Yeah, this generator is R, and now you have to see what what is annihilated. What annihilates that element? In other words, what knocks it into here? So X times it is certainly in there. And but that's really all. If you think of no other polynomial will it be inside of this subspace, submodule. So that's X1. What's X2? X2 is computed here, right? So what's X2 of R mod I into R? This one's actually interesting. The very last one is always interesting because at the very end, it's going to be everything goes to 0, and it's just mod this. So this is really going to be, I haven't figured out a degree here. We should probably figure out what it is, because this is not in degree 0. So the question is, what degree is this element in? Z, Y, Y, Z. What? Yeah, the generators here have degree -2. So when you multiply it by Y and Z, it's degree -1. So this is going to be a -1 here. Okay. And I can put the R mod X and then put the -1 after it or before, it doesn't really matter. Okay, so what is this one though? X2 is everything modulo the image of this. So what is that? I guess it's R of. Actually, I'm a little, wait a second. This one, -1 is incorrect. It's 1. This is a 1 here. Because I said the generator was in degree -1, which you have to give the negative of that number as the twist. So what is this one? It's R of 3 modulo the ideal generated by Y and Z. Okay. Kind of interesting. What is this thing geometrically? Yeah.
Alignment.
Exactly. So it's X equals 0, union Y equals Z equals 0. So it's X equals 0. I guess that's a plane or a line, depends if we're doing it projectively. And the other one is a point. So or a line. But if you see it, these two things are actually this one has the Y and Z in it, and that one has the X, which is the other component. There's a awesome theorem floating around here somewhere, which we have to maybe figure out. So there's we are going to talk about soon. Actually, we'll be talking about primary decomposition and things. And one way to think about it is in terms of these X and all the minimal the associated primes. They kind of bubble up to so you can actually see them. It's there's some really cool, kind of cool stuff. I got to say it's really not the way to compute these things most of the time, but it's nonetheless sometimes when it does work, it's very cool. Okay, so what else was there? Should we actually calculate the Hilbert series? Did I actually suggest that? I did. Let's see. We'll go back over to this one. So what's the Betty table of this thing, by the way? I think it's good to do these simple ones by hand just to sort of see what's going on, because once you start doing it by computer, you kind of start losing the thread sometimes. So I think it's good. So anyway, so what is the Betty table of this? So there's one element in this is in the 0 spot, the first spot, and the second. I think that's all we have are those. And then we have degrees 0, 1, 2. I don't know how many degrees we're going to have, but that's not going to be the. These are just indices that we're going to use. So this one is the R right there. Where does the R minus 2? 2? It's going to be a 2 because there are 2 degree 2. It's 1 here. That's the minus 2, and then 2 of them is here. Okay, so that's this value. And then when we go back here, we're going one more linear thing. So we just so we're going over. We're over here now. We go from here up 1. So we have a 1 here. So this is the Betty table. Okay. Now let's and so I would put these here. Those are all 0. Okay. Now we want the Hilbert function of this R mod I, or the Hilbert series, say. So let's do it. It's going to be here, here, and here. It's going to be this one minus this plus this. So the first one is, and it's all going to be over 1 minus t. How many variables was I in? 3. So I'm in this. And now, so that first one, that R is just a 1. Okay, now for generators, I have 2 generators of degree 2. So this is an R minus 2, direct sum R of minus 2. Each one gives me a t squared. So I have, so this 2 here is going to give me not a plus, a minus, because it's alternating sum, minus 2t squared. And what's the next one? It's going to be a plus. And then that one is a r to the minus 3, which gives me a t cubed in the numerator. So this is it. And then sure enough, if you see this, you can divide by 1 minus t, you get 1 minus t squared. And here you get, I don't know what you get. Something. I don't feel like calculating it by hand in 30 seconds or whatever. Did anyone compute it? Something's fishy. because this negative here. This would mean somehow that the degree is negative. But wait, if I take this thing and I multiply it by 1 minus t, do I get this?
Squared minus t minus.
T squared minus t minus 1? Oh, I see. If you divide by t minus 1, then you're going to have a negative value. So yeah, actually that is true. That if you divide by 1, it will come out somewhat. Is this a negative like that? Is that what people got? Okay, something like that. We can run it through Macaulay 2 and just do the division. Or whatever. But in any case, but this is kind of cool. This 2 means that this thing has dimension 1 as something in projective space. That makes sense. It's a line union a point. And so that line is giving us the dimension 1. And then the numerator is whatever it is. You know, each one of these things translates into a nice binomial. The Hilbert polynomial is also pretty easy to write down. You can write down the Hilbert polynomial for any one of these things really trivially too. And then the Hilbert polynomial, this is just the alternating sum of those things. Trouble is that writing down an alternating sum of binomial polynomials is a mess. So in some ways, that's why I kind of prefer generally this. What, by the way, would happen? One more thing. Suppose that this came out to be a 1 here. Okay. Let's actually not do that. Let's do it this way. Suppose that, in fact, the Betty diagram was like this. It was 1, there were 4 generators and 2 linear syzygies and 2 cubics and 4 and 1, or, you know, something like this. Okay. What's the Hilbert series of this one look like? So this one is going to give a 1. Here we get a minus 4t squared because it's in the 2 spot. Okay. But here we get a minus 2t cubed, minus 4t squared minus 2t cubed, but this is going to be a plus 2t cubed. So these two guys cancel each other out in the Hilbert series. So the Betty table is strictly more information than the Hilbert series. And then it's going to be plus 4t. Now this is going to be t to the 4th because this is degree 2, 3, 4, and then minus t to the 5th or something like that. I don't even know if this exists as a probably doesn't. What?
But same thing as before. Oh, no, it don't answer that one.
This should, but actually, to tell you the truth, I just wrote this down. This is a one. It's an interesting question: does this Betty table even exist? Can you find 4 quadrics and 2 cubics that give you exactly this? Yeah, maybe. Maybe not. So there's a lot that can be said about that kind of stuff. So one of the things I did give you guys, it's time to go. I'm going to let you go, but take a look. Try to use Macaulay 2, the bit about trying to find lots of examples. Just do lots of random, or maybe not that random, ideals generated by 4 quadrics, and let's see who can get the most different Betty tables for that. For 4, it might be known. For 5, the number is not known, I think. So at least no one's actually. It's a reasonably large number. So my challenge is get as many 10. Let's see how many we can get for the 4 as a group. We'll compile them all together or something like that. And then for 5, I want to know how many. I can't remember. Oh, the input is you take 4 quadratic polynomials that are homogeneous quadratic in any number of variables, and you look at their free resolution, and you get a Betty table like one of these things. And then you just see how many different Betty tables you can get. For that one, they're always going to start like this: 1, 4, and there will be nothing else in this degree because it's just generated by 4 quadrics. And then if there are any linear syzygies on that, that'll give you a number here, or quadratic will give you a number, or cubic, it gets hard to have. So there are bounds on how far down you can go, but a lot of them are not really understood, gotta say. There are a lot of interesting open problems along these lines, and also how far back it can go. Well, if you're in 10 variables, it maybe could go back 10 stops, spaces, but it can't. So, well, there's a bound. And for 4, I think most everything is known. You can even enumerate all the ideals like this, but it's not trivial. Even there, it's really not trivial. But for 5, it's not known.
Doing this
I was doing it, Macaulay.
and you're always gonna.
No, well, it doesn't really matter. The finite field, if you do it over the rationals, and you reduce it mod a finite field instead, as long as you choose almost any prime, you'll get the same Betty table. So, so it's not like you're changing it that much. You're just making your life a little easier. The degree of this should be 1. And that's because we have a line. And that's a degree 1 object.
So if we got 10 terms.
You could have 10 terms in the quadrant. Yeah, it doesn't seem like it should be that bad, right? So if you're in 4 variables, you can maybe do it. But what if you're in 10 variables? You know, it starts to get to be a needle in a haystack to find. Right. Oh yeah, so do it. You can do it in Zmod 5 or Zmod 3, and you'll probably find all those ones. Maybe you get a couple extras.
Like exhaustive searches.
Yeah, but over Zmod 101, it's going to be hard to do an exhaustive search. There's a lot of things that you can do to cut it down. So it's certainly possible that one could do it, but I got to tell you, the number in I don't know the exact number I've found, but it's around 100 different Betty tables. So it's to actually classify all. That's for 5 quadrants. So to classify them all is a little tricky. It's just going to be a complicated kind of thing.
So is a common in Macaulay to simplify the inverse series?
Oh yeah, it's called reduce Hilbert, and it will get rid of as many of these 1 minus t's as you want. That existed before other facilities were around, and just tend to use it. So it's nice because it keeps things in factored form and so on. Okay, thanks everyone online too. See you next week.